Should we start or wait for some of the other folks to start? Okay, good morning everyone. Welcome to day 4 of this GIAN course. So the first 6 lectures, what we had covered was most of the technical aspects of model development, or how do we apply these models for different clinical use cases. We looked at the first day we looked at radiology informatics. The second and the third day was focused on digital pathology or pathology informatics. So today and tomorrow, for my parts of the lecture, we'll segue a little bit and cover some of the non-technical aspects. And by that, what I mean is, it's not that just because it's non-technical, it's not important. In fact, in some sense, it's more important than the technical aspects. That's because what we'll be covering in these 2 lectures today is you have developed your models, you have developed your AI systems. What are the different factors that we need to consider before and during deployment of these AI systems in the clinic? And this holds good not just for AI systems that have been developed for medical imaging applications, but these rules and these concepts that we'll cover today will also hold good for AI systems that are in the non-medical domain. So let's say that you're working on some sensor-based technology that will be at some point used in the clinic, right? Or some large language models that you'd like to deploy in the clinic. So there are some of these commonalities between different domains that lie in the themes that we'll be covering today in today's lecture. So it's titled Clinical Considerations for AI Deployment. So what we'll be doing is, so when I say the different considerations, we'll be looking at some of the practical aspects, right? So for example, what this image covers here today, what this image here, what are the different factors that I have in this image. So clinical workflow fit, what do you need to do for validation and generalization? Right? So interpretability and trust, some parts of it we covered yesterday. Regulation and governance. So we'll touch on some of the regulation and governance part tomorrow, but these are different factors. Human AI interactions, we touched on that, and then how it's all reliability over accuracy. Before that, so I have this, so if you look at the last line here, I say that performance enables deployment, reliability enables adoption, right? So what does that mean? So take a step back and think about it, right? So in fact, I went out with some of you guys to watch Dhurandhar last night, and any of you actually liked the movie? Yes. Many of you did, right? So one of the themes that emerged in the movie, and if you think about it, the way the spy intruded into the enemy camp, or in fact also how Rehman Baloch he tried to make a name for himself. So if you see how that happened, so power got them noticed, right? So it got them noticed, but sustenance, how they performed over time, that got them credibility, right? So if you think about AI systems, it's a similar thing. If you build a system where your performance is great, it'll get you noticed. But if your performance is reliable over time, if your model can adapt to new settings, that is what will drive adoption. Okay, so it's just an analogy between what we'll cover today and the movie Dhurandhar. So objectives. First, AI models in radiology will cover. We have already covered some of it. AI models in radiology and the clinical applications. Next, we'll be looking at how to understand the challenges of large-scale enterprise-level deployment of AI solutions for radiology. Thanks. And then finally, we'll look at post-implementation evaluation of these methods in clinic. So by that, what I mean is, once these tools and techniques have been deployed in clinical practice, what are the different evaluations that need to be done? It's not that if you have a system, you deploy in clinic, you deploy it and you forget about it, right? So especially in AI, because these models are getting better and better, you will have new data, you will have different kinds of, let's say, corner cases that doctors will encounter, false positive, false negatives, which they might not have seen previously. All of these can be used to improve the model, right? So these are the things that you have to account for when or after the model has been deployed in clinic. So when you look at this AI model development life cycle, so what are the different things that come to your mind? So when it comes to taking an AI model, developing it, validating it, and deploying it in the clinic, what are the different parts of it? So it's not just a simple process where you fire up your Google Colab, or let's say you have your interface, whatever interface you're working on, you develop your tool and you immediately deploy it in clinic, right? So what are the different development milestones? And there are multiple. So maybe we can start a discussion here. So anyone? So what do you think is the first step of this development life cycle?
Data preparation.
Okay.
Data preparation.
Okay, so what do you mean by that? What do you mean by data preparation?
Data normalization, pre-processing, and all the like cards out of
so
data.
normalization, pre-processing. What about a step before that?
Data collection.
Data collection, right? So you need to identify a problem and you need to collect the data for that, right? So first is identification of the problem. So you need to identify what the use case is. So let's say that you're working with radiologists. They say that one of the use cases that they want to, or one of the clinical unmet needs, is segmentation of some kind of a lesion, right? Maybe it's a very small lesion or a rare disease. So they want to detect it. They want to identify it. So you identify the problem first, right? Now, after you have identified the problem, that's when you start collecting the data. Right? So a data collection and preparation, like you said. So you have to collect the relevant data. So you need to know what sort of cohorts are, let's say, representative or can be used to rightfully answer that question. Right? So you need to know that. So also what happens is, and we'll cover a little bit about that in the later slides. So it's not just collecting data from that one site. So ideally you would want to collect data, or by one site I mean it's not just a homogeneous thing, right? So you would like to collect data from different populations of the same disease, right? So let's say I briefly touched upon this a couple lectures ago. You have let's say African American populations, Caucasian populations, and then you have people in India, all of them having the same disease. It has been shown in multiple different studies that models trained on one population, on one race, doesn't really, or doesn't generalize well to data collected from another population, right? So if possible, we need to collect data with as much heterogeneity as possible. So next step, model development. So choosing the right algorithms and designing the model structure. Okay, so you have to choose, so there are multiple different algorithms that you can choose from. So which is the best algorithm to go with? Like, do you go with something that's more recent, more fancy, or do you go with something that is more tried and tested, right? So a lot of times what happens, and you'll realize this over the course of, if you are into research, you'll see that the fanciest methods, the more sophisticated methods, they are not the ones that give you the best answers. Sometimes very simple solutions can be the elegant ones and can actually help you solve the problem that you want to solve. Okay, so once we have identified the problem and collected the data, prepared the data, in fact, in data preparation, there are a few steps that you mentioned, pre-processing, right? So before pre-processing, in fact, it goes hand in hand. You need to do a quality check, right? So at times there will be a lot of outliers. If you remember in the whole slide images, I said we covered how there might be outliers like cracks on the slides, or there might be some air bubbles, or there might be out of focus regions. So in radiology images, you can have different kinds of artifacts. So one of the artifacts is in the MRI machines, if there is patient motion. If there is patient motion, what happens? Okay, so what would happen if there's patient motion? Anyone? So in these MRI images, show of hands, we can use the mic. So you saw these brain images, brain MR images, right? So what would happen if the patient moves slightly?
I think the images would have multiple instances of the same organs.
Yes. So what happens is you'll see some sort of artifacts where you'll see sometimes it's called aliasing. So you'll see, let's say, the skull appearing multiple times, right? So there'll be a lot of noise. So we need to have pre-processing steps that can account for and that can correct for this noise. And like you rightly mentioned, we need to do some sort of harmonization. So if you remember in the earlier step or in the data collection step, ideally we would want to collect data from data with as much variability as possible. So what that means is you could have data from scanner 1, which is a GE scanner, scanner 2, which is a Philips scanner, scanner 3, which is a Siemens scanner. So you can have multiple scanners. And at times you'll see that when the same patient is scanned with different scanners, or let's say the tissue of the same of a given a patient of a given tumor for one patient is digitized with multiple different whole slide image scanners, you'll see the quality of the images are slightly different. Okay, so what does that mean? So that it's the same patient. The disease is still the same. When the doctors look at it, the doctors will still hopefully diagnose the exact same disease. But what we want to make sure is that the computer, when we give these images to the computer, we have to make sure that they are sort of normalized, harmonized to the same space, and have as little variability as possible when it comes to providing images from multiple different sites. Okay, so what could be the next step after model development? Training is the model development, right?
Then testing of the model.
Right. So you need to do a model training, and then you need to have a testing. So by testing, so there are multiple steps. So sometimes you'll see that validation and testing are used interchangeably, but and this is very important, in the context of machine learning, training, validation, and testing are 3 distinct steps, right? And we'll cover about that in the next few slides. So let's see what I have. Yeah. So model training is once you decide what model you want to use, and let's say you have some sort of, there are multiple parameters that you have in your model. You have different strategies for training, for identifying what the parameters are. So model training will actually have, there'll be multiple parameters that you can have in model training, right? So there are algorithms like grid search algorithms or other kinds of algorithms that can be used to identify the right set of parameters. Now, once you have done that, you want to validate it. So how do you decide what the best set of parameters are? Like there'll be, so let's say that you have an equation, right? Ax plus by equal to c, right? So you can have multiple values of a and b, for example. So how do you decide what the right values are, or what the best values are that give you the best estimate of c? So that is something that you decide in your validation step. You do not touch your test data set. Your test data set remains completely untouched, right? So you finalize your model parameters on your validation set, and once you're happy with your validation performance, that's when you go to your test set. Okay? So a lot of times you'll see that, and this happens, more times than I can count. If you look at the way people, a lot of papers are written, when they provide the results, you'll see they run the different models which have been run on the validation set. They basically take those models with the different parameters and run it on the test set. Right? That's not what should be done. If you have a test set, that should be completely held out. And once you're happy, provide your validation set results with your standard deviation, obviously, because when you run different models, you will have slightly different performances. So for those of you who are working in wet labs, so let's say that you have developed some sensors. When you test that sensor to collect a reading, it's almost likely that every time you collect the reading, there'll be some error. Right? So sometimes, so let's say you're collecting the blood pressure, you'll have a particular value x, and the next time you'll have x, you'll have y, next time you'll have z, and these might be slightly different from each other. Right? So what that means is that when you report it, you will have to report the average value. You also have to report the standard deviation. Now, when you report the standard deviation, if the standard deviation is really high, what that means is most likely your sensor, your model, it's not that good. right? It's collecting, it's giving you readings which are way off from each other, assuming that nothing is changing with the patient, right? So ideally, the confidence interval, the standard deviation should be low within permissible limits, and that's something that you have to decide depending on what your application is. And that standard deviation basically decides, how robust the model is. But once you have done that, you take, whatever the best parameters you have from the validation set, test it on the test set, and show the results. So you can test the model's performance and refine it for better accuracy or better AUC, better F1 score, whatever your metric is. And after that this is where things actually start getting real. They start getting out of the papers that you have published, right? So model deployment. So when you start deploying the model in a real clinical environment for a real world use case, that's when you actually observe that nothing works, right? So you go from your test environment, from your lab to the clinic. That's when you see that, okay, what I did, I probably need to redo, or things have to be done differently. The reality of what's there in the real world is very different from what's there in the lab. And so once you have done your due diligence, once you have, let's say, arrived at a model that actually works well or works as expected, you need to monitor and maintain, right? So a lot of times you have things like model drift. So you need to continuously monitor the performance of the model. So let's say that I am a vendor, you're a doctor in the clinic, you have purchased software from me, and you are working with that software. It's not like you purchase that software, you keep running or providing images to your software, getting decisions and using it. I need to know what's happening with it, right? So I need to know if it is still working as expected. I need to know if the errors that different kinds of artifacts or the errors that the model is actually giving you, if that is within your permissible limits, or something is happening with the model that is not expected. So you need to tell me that, I need to know that, right? So it's a two-way street. So only then can you, or only then can I as a vendor, as a model developer, can make sure that my model is up to date with the latest requirements, and also the onus equally lies on the clinician to make sure that that happens. Yes.
So after model deployment and during the monitoring phase, can we also collect some sort of input and maybe for segmentation example, some segmentation information, so to identify such drifts if any of that happens?
So that's an excellent question, and that is something that should be done. A lot of companies do that, but many companies do not do that. So his question is, when the model has been deployed, while it is actually being used in the clinic, should we or can we collect data regarding, if it's a segmentation model, can we collect some, let's say, examples where the model fails, or if the model has failed, can we ask the doctor to, let's say, correct those segmentations and give it back to the vendors, to the model developers, so that they can improve it, right? So that's a question. It's if you think about it, that's how it should be done, because otherwise, how will the model developer know that the model is causing an error like that, right? So that's exactly what I meant when I said that, yes, the doctor has to communicate with the vendor and vice versa, so that we know what's happening. If there is some way that we could help you, if you can provide us, let's say, some of these outlier cases or some of the cases where the model does not work as expected, maybe correct the segmentations for us, give them back, then we can fine-tune our model on these kinds of examples so that it gets better. So I mean, it's easier said than done, because this is medical data. So there's a lot of ethical challenges involved here. We'll cover ethics in medical AI tomorrow. So eventually, you you will be giving, so just a teaser. So this is patient data we are talking about, right? So you have to give the vendor, so the software exists on your side. So it can either be a cloud-based platform which has, all these ethical requirements, let's say satisfied. So in the US, we follow the HIPAA regulations. So but if the model training most likely goes on at the vendor's end, right? So I have my own GPU, I will train a model, and when I deploy it, I'll deploy it in the cloud, a secure cloud environment, or I'll deploy it on-prem on your machine. So, but if you want to give me data, if you want to give me patient data, that means you'll have the patient's name, you'll have the clinician's name, you'll have other kinds of sensitive information. So that actually intrudes on the privacy, right? So it's a very big thing. So back in the day, maybe 10, 15 years ago, that was probably not that big of a concern, but it's getting quite serious nowadays. So there are mechanisms of doing that. There can be, some sort of a material transfer agreement or data use agreement that I as a vendor can sign with you as a doctor, and then which ensures that I get the data, but I don't share the data with anyone. Or you give me the data, but you remove all the personal information, all the identifying information before giving me the data. Right? So we'll cover that tomorrow. But yeah, like I said, it's easier said than done. But that's how we should be doing it. So also, I'm sure all of you here would have used ChatGPT, right? How many of you have actually gone on to the settings page of ChatGPT and seen that ChatGPT is actually training on your data? Yes. Is everyone aware of that?
Yes.
Yeah, let's use the mic. Yeah. Interestingly, my students were not aware of this as well. Yes,
When you buy subscription for like any of this, like Perplexity or any of the AI model, they in their terms and conditions it is written that we use your data.
Yeah, so they do that, and also there is, if you go into the settings I know this is being recorded. So if you go into the settings of a lot of these LLMs, you'll see that you can turn off that setting, that don't use my data for training, and progressively you'll see it's getting difficult to find out where that check option is, right? So which means they're clever people, so they train on the data that they get. So we have to be careful. I mean, it's not that we don't have the provisions of telling the models not to train on our data. We have these provisions, but you have to be careful on what sort of data you want the model to know to be fine-tuned and so on. Okay, so coming to the first part, there is a need finding and a planning stage. You need to identify a true clinical need, like I said. So you need to know, you need to discuss with the clinicians, they need to show you images. It's not like they tell you, okay, I need a model for XYZ segmentation. That is not enough. You need to sit with them, you need to talk to them about, there will be obviously more traditional problems where you can query literature, you can find out what that problem is, and maybe you can start identifying and training models on your end. But with a lot of these new problems that crop up, new clinical unmet needs, you need to sit with the clinician and understand what that problem is. They need to show you images, they need to show you some sort of data and convince you that this is a problem that is worth solving. And it's not just that. You need to look at the data and you need to decide whether that is something that can be solved, right? So let's say that so just a hypothetical scenario, there's something in the image that needs to be found, but human beings cannot see it at all, right? If human beings cannot see it at all, or experts cannot see it at all, your machines can't also see it, right? How will a machine find out something that an expert cannot? Because eventually you want to get segmentations, you want to get some sort of annotations. So if human beings cannot see it, if experts cannot see it, you cannot get enough annotations. Or you cannot get, let's say, good quality annotations if it's a very, very, very difficult problem. And if you cannot get good quality annotations, then it's almost asking too much of a model to find that out, right? So you have to make sure that it's a model So the clinicians have to convince you that this is a problem that's worth solving, and then you have to convince yourself that, okay, there can be enough data collected, or this is a problem that machine learning can tackle. Okay? And then determine a decision action pair. So this is again where both clinicians and AI developers should work hand in hand. So what does that mean? So if you suggest something as an AI developer, or if your model suggests something, what clinical decision does it lead to? Right? So that has to be very clear. So does that lead to, let's say, changing of the treatment, or is it just an additional read for the radiologist, for the pathologist? So how would it change the clinical decision workflow? So that is something that you need to understand. Third important thing, you need to consider factors at the site of deployment, right? So I mean, yes, nowadays a lot of these deployments are on the cloud, and which means that doesn't really matter if you are at Rourkela, or if you are at Bhubaneswar. Eventually, if you use the same cloud setting, then you will have access to the same resources. But you should understand that cloud deployment is costly, right? So for those of you who have used GPUs on the cloud versus GPU in your lab, local on-prem devices, you will know that cloud deployment is costly, right? So which means that a lot of the different hospitals, a lot of the different what ends up happening is they prefer to have on-prem solutions. And it's not just because of the cost associated with the cloud, but also other kinds of, let's say safety regulations, or there might be other factors that they're a little wary of, so they don't want to put their data on the server. They want to keep everything at their end. So because of all these things, and all of these are valid concerns. So because of this, they might want an on-prem installation, or they might want a hybrid installation where they have part of the installation on-prem and part of the deployment that's done on the cloud. So you can have different kinds of deployment scenarios, and if you want to have some sort of an on-prem deployment, that means it's important to know what sort of resources you have on-prem, right? Do you actually have computers that have enough computing power? Do you have enough GPUs? Do you have enough CPUs? Right? Do you have the technical personnel, or the personnel who you have? Do you have the technical, let's say, expertise to help you with this? Right? So a lot of these factors, many of these factors need to be considered at the site of deployment. Any questions so far? Yes.
Sir, my doubt is regarding the annotation. So if I am using a software to do annotations regarding to visual segmentations, so is it a good practice, or it is a go for the clinical is good?
So I didn't understand your question. If you are using a software to do what?
Annotations, sir.
Yes.
Annotation for these images.
Right.
Is it a good practice, or with the consultation of radiologist is good practice?
So again, so what do you mean? So you are using a software for
Image software I am using, sir.
Image
J
okay.
software I am using for the annotation of the image.
Right.
So is it a good practice or not?
So it depends on what you are trying to annotate. So let's say that you are trying to annotate radiology images, so for your research purposes, and then you want to develop your AI models. I don't think there's a ImageJ. I mean, yes, ImageJ is good. It does provide you a lot of functionalities, but software like ITK Snap or 3D Slicer that you saw yesterday, those are the ones that provide you, let's say, more flexibility when it comes to collecting these annotations, saving them as multiple different levels, 2D, 3D, doing some analysis on that. Yeah, so that is what I would recommend. But a lot of times people have used ImageJ, but they are mostly for more, simpler images. Okay. Any other questions? Yes, so one more question here.
You told about hello. So sir, you told about the material transfer agreement,
Yes.
MTA.
Yes.
So sir, my question is, when we are going for the hybrid solution, or when we are giving the cloud setting for the considering the factors and site of deployment you told. So in that case also material transfer agreement will be a major concern, because first of all it is costly, the material transfer agreement, getting all those agreements, it is costly first of all, and also when we are deploying it into the cloud, it is also costly. So in that case, I think cloud settings should not be a better option.
So it again depends. So I see what you're trying to get at. So it all depends on what you need, what your enterprise can support, right? So if, let's say, your task is very compute heavy and you do not have those kinds of resources, or you cannot, you don't have the budget for those kinds of resources, then you would, resources as in the cloud, then you would probably buy something that's a little bit cheaper on-prem. But if you have those budgets and you don't want to, deal with the hassle of having local IT maintain these things, then I think a lot of places go for cloud deployment. Yes, the MTA, the material transfer agreement, or the DUAs, the nature of it will change, and I can't really talk much about that because it's more legal in nature. I'm sure, like in the MTAs, in the DUAs, you will have proper terms and conditions that tell how it should be used. So let's say that you are using something to transfer data. So I'm sure you've used Dropbox or Box, something like that. So there are HIPAA controlled storage devices, which means that these storage, by storage devices, I mean these HIPAA controlled cloud storage that still let you upload clinical data. It's okay to have patient names. It's okay to have identifying information, but you cannot do that on Google Drive. Okay, so Google Drive, there might be, I'm not aware of it, there might be versions of Google Drive where you can do that, but typically people don't use Google Drive for uploading patient data. Okay, it's not HIPAA compliant, at least on our end. Okay, but yeah, you are right. The complexities of how these agreements are written and executed will be very different if you have on-prem versus on cloud.
Thank you, sir.
Yeah. Okay, let's move on. So dataset curation, image pre-processing, and annotation. We covered a little bit on that. So when you collect your dataset, you need to anticipate potential biases, and we covered how different kinds of demographics, different let's say different population settings can have slightly different image presentations, which means that when you collect the data, you need to have different as much heterogeneity as possible. And however, okay, so even though I say that we should do that, but a lot of times what happens is, just because of the nature of the problem, it's not possible to get that kind of data, right? So let's say you're working in a lab, your PI tells you that, okay, this is a problem that we have to solve, here's the data, right? You need to get started somewhere. You need to start developing these systems, and then at some point when you let's say you are ready to start the translation process, that's when you start having these discussions regarding these different kinds of heterogeneity if your data set already does not have it. Also, when you look at clinical papers, I'm not talking about technical papers, so if you look at machine learning papers or vision based papers, you won't really have this analysis on how this model performs on males versus females, or how this model performs on different let's say age groups, right? So less than 20 years, 20 to 40 years, 40 to 60 years. So this is probably not that important when it comes to technical papers or vision papers, machine learning papers. But when you look at a lot of the clinical papers, high impact clinical papers, most likely, or I think almost 100% of the time, you will see that the first table or the first figure that they will have in the paper will be about the data set distribution, will be about the demographics. What is the age distribution of the patient? What is the sex distribution of the patient? Does the patient have any kind of comorbidity, right? And also other kinds of factors. If you have the race of the patient available, like you have to summarize the race of the patient. So the reason these publications, these clinical publications, want you to have this information is that when you train your model, or when someone reads your paper, they should know what kind of data set your model was trained on, right? So for those of you who have worked on medical imaging, do you consider this, right? So when you write these papers, clinical papers, if you have to consider these data distribution aspects. Okay, so curate data set from multiple sites, like I said, to ensure robustness and generalizability of the model. and then we have to standardize the annotation, de-identification, and pre-processing. So standardize the annotation, what does that mean? So a lot of times what happens is you need annotations for training a segmentation model, and let's say your data set has 500 images, and these are 3D images. And getting 500 annotations from one person, from one expert, might be very expensive or might be very time consuming on the expert's part. So what happens is you divide the work, right? You have 3 different experts. You say, okay, take the first 20 images, or take the first 100 images, take the second 200 images, the next 200 images, and please annotate them for us. Now, if you do that, just think about it. That means that you are invariably infusing some sort of subjectivity there, right? Because clearly the first expert will be slightly different from the second expert. Doesn't matter how much you tell them that this is a protocol you have to follow. We are humans, so it's humans. Bless you. If it's human nature to err. So we will at some point see that there will be differences, despite the set protocols. There will be differences in the nature of the annotations that you get. So that's why we need to standardize annotations. And what does that mean? So yes, identify a protocol. Tell your experts that this is a protocol that each of you has to follow, so that to the best extent possible, we make sure that they are sort of standardized. But after that, you need to have some sort of a more expert reader. Like if you have 3 experts, you need to have a super expert, and they need to quickly go through all the annotations and see if some major change is required. Then what you can say in your work, or ideally what you should do, is you can say that 3 experts were involved in the annotation process. The data was split equally between them, and the annotations were after that verified and corrected by a more senior expert, right? So something like that, if that's possible. The other way that could be done is, and that this is usually done when you don't have a lot of data. So let's say that you have 200 samples, and you want to minimize variability. So what you can do is you can have the 200 samples annotated by both the experts. So if you have 2 experts, you have both the experts annotate the 200 samples. Then you do some analysis to figure out which of the samples there was a lot of disagreement on, right? Then you go back to the experts and say that, okay, these are the 10 samples where you and you, like A expert A and expert B, did not agree on. Could you please talk to each other and see what should be done? And this is mostly true. Segmentation, it's okay, because sometimes segmentations are off by a few pixels, which probably won't matter a lot. So I take that back. It will matter a lot depending on what the eventual use case is, right? But let's say that might not matter a lot. But if it is some sort of diagnosis, if the experts differ on diagnosis, then we have to ensure that the model is trained on the right diagnosis, right? So that's when you have to get the consensus of the experts. So that's why you'll see that when it comes to the dataset curation step, you'll see a lot of papers, they say that this decision, the ground truth, was arrived at based on consensus between the experts. Okay, any questions here? So all of these things are important. I know that when you get your data, you want to jump into training a model, but as you get deeper and deeper, as you get further in your research career, you will know that these are the things that are more important. And I mean, I can say that when I started as an enthusiastic student, I was like, okay, I want to train my first model. I want to train my model. I want to get papers done. I never stopped to, or I never paused to think about how these things can actually affect the downstream performance. But over the years, I've realized that the sooner you do this, the better it is. Okay. Cool. So if you, do you have any questions on the previous slide, by the way?
Sir, my question is about the pre-processing and stuff.
Yeah.
Actually, I have seen like more people, those who focus on like model development and training, and then they follow the other papers work very closely with the model development, like training and stuff and all. But they more often than not, they try to ignore the pre-processing step, and then each paper follows a different pre-processing step. Like one way or other way, they'll just change, and they don't actually give the complete details of how they have pre-processed the data. And then like I'm not sure like how it affects the processing, but because for me like the pre-processing has affected like very much. So like what kind of suggestion do you give for the people who are involving this machine learning and deep learning? So what kind of step do we have to follow for the proper pre-processing and stuff and all before training?
Yeah. So the pre-processing obviously depends on your modality and your application. So for example, in digital pathology, you have pre-processing steps like color normalization. For radiology, if it's MRI images, you will have pre-processing steps like intensity standardization. A lot of times you have registration. So in brain MRI images, you have to register everything to like a common atlas before you do your downstream tasks. So these are all pre-processing steps. And you're right, a lot of papers don't give out these details, but you'll see that high impact publications will have these details. Doesn't matter if it's there in the main paper or in the supplementary. If they don't have these details, I'm sure it won't get accepted, right? So it's a very important point, and this is for all of you. When you write your papers, you have to provide your pre-processing details. Obviously, a lot of times your papers will say, okay, it's a 8-page limit, 6-page limit, you don't have enough space, but they will accept supplementaries. So you provide this detail in the supplementaries. But what I've observed is that especially a lot of these new machine learning papers, these foundational model papers, they don't have details regarding that, because their argument is that because it's a foundation model, the foundation model should see as much variability as possible, right? So according to them, these initial pre-processing doesn't really matter. And you can see why their argument might hold true, because in some sense you would want your model to perform well on variety of data. But eventually when you want to go towards model deployment, and let's say it's a niche case, you have to do this pre-processing. At least if you use the foundation models, you are not using the foundation models as is. You will do some fine tuning after that. You will just use the foundation model as a feature extractor, right? So, but I think we should be doing the pre-processing that we are doing for a real clinical model. Yes. Yes.
Sir, you told about like getting the consensus of both the experts. So in day 2, you while like teaching us the radiomics analysis, you told that like if there are two like reader who like one is giving 42% and another giving maybe 50%, and we are like annotating it with the machine learning reads, and we are getting the, after doing the radiomic classifier, we are getting the like it is 92% or something, like it is giving the more eligible. So sir, my question is in which respect we go for the consensus of both, like both the reader or the pathologist, and in which aspect we go for the machine learning?
Okay, so good. Someone is actually following my lectures. What he's saying, there was a slide in my, I think in the very first day, where I said that radiologist 1 was I think 42% accurate. Radiologist 2 was 50%, yeah, 50% accurate, and then the machine was 75% accurate, right? So his question is, when do we go for a consensus? When do we go for the machine read, right? So these figures that we saw on day 1, this was for the in the inference stage, in the test stage. What I was talking about today is the training of the model. So to get ground truth of the model, what I was saying is we need to get some consensus, right? Because if radiologist 1 says that this case is cancer and radiologist 2 says that that case is benign, what label will you take for your model training, right? Like you don't know. So you have to talk to your radiologist, ask them to go for look at it, go for a consensus, and then see if they can arrive at either a cancer or a benign decision. Now there might be cases where they still cannot decide, right? But that usually will not happen, because eventually you will have some like the patient would have been treated, right, based on whether they had cancer or did not have a cancer. And they will have, let's say, some pathology, biopsy or resection done for confirmation. So you will have that information. If you don't have that information, what a lot of models do is you can consider them as, let's say, independent samples to some extent, and you can ask the radiologist, how confident are you that this is cancer? You can ask the second radiologist, how confident are you that this is benign? So maybe you can take that confidence into account with the label, and there are methods to do that as well. Okay?
Okay, thank you, sir.
Okay. I'll cover a little bit about how to get more labeled data. Obviously, it's not possible to get infinite labeled data. It's very expensive, like we saw. So obviously, one way is traditional supervision. You have your experts annotate as much data as possible. And the second is semi-supervised learning. So you use some structural assumption to automatically leverage unlabeled data. So for some data, for some of your data points, you have labeled data. For some of your data points, you do not have labeled data. So it's some sort of a semi-supervised learning, or if you have partially labeled data, that's semi-supervised learning. You can also have weak supervision. So a lot of applications, a lot of not clinical use cases, a lot of methods are developed with data that are with annotations that are weakly supervised. So by that, what I mean is, so let's say that you have an image, a brain tumor image, and you have a brain image, and you have a tumor somewhere here. So let's say that it's very difficult to get these segmentations from the experts. Or you have an X-ray scan. Let's say you have a lung X-ray, a chest X-ray scan. You have the COVID infiltrates or the pneumonia somewhere here. It's very difficult to ask the radiologist to go through the hundreds or thousands of X-rays that you have to annotate where the lesion is. So what you can ask them to do is, okay, let's not do an exact annotation of where the disease is. Can you just put an arrow that this is where the disease is? Just put an arrow, or just draw a line, right? Or just do something like a small squiggly sort of a sketch. Okay. So a lot of methods are developed with this sort of weak supervision. You don't have the exact annotation, but you can still use this weakly supervised annotations to train your models. Okay, and we have also done that. We published a paper in ICLR a few years ago that does this. And then transfer learning. So if you remember, I showed you the slide where we were using a pre-trained model to generate blood vessels. So that was a transfer learning setting where you use another model to train whatever segmentation task you want to do, and then you transfer the weights and you basically generate your segmentations on the new data set, and then you can use techniques like active learning or uncertainty analysis to identify only the areas, only the, let's say, the regions of interest that need to be corrected by the radiologist, by the pathologist, and only provide those limited regions to them, right? So there are these methods that you can use as well to get more labeled training data. Okay, so once you have your whole data set, you need to divide your data set into training, validation, and testing. So there are different ways you can do this, either a 70, 20, 10 rule, or it depends. So a lot of times your test set is completely independent. If it is completely independent, you can divide your training and validation into 70% and 30%. So it all depends on how much data you have. Okay, so in the training set, what you do is you teach the model patterns. You teach the model the patterns in the data, and the model learns the task. And in the validation, you tune the model. You identify the best parameters, and you choose what architecture is the best. So let's say that you have, with vision transformers, you can have different, let's say, variations of these transformers. So you can have small versions, you can have large versions, you can have huge versions. So depending on how deep the network is. So you can have different complexities of the architecture. You can try all of them out, but they have to be validated on the validation set. You have to decide the parameters and then just stop at the point where you think that this is the model that you want to use. So you have to lock your model down. Okay. You have to make sure that it doesn't overfit to the training set. So a lot of times when you train your models and you can try this out. Start with a simple deep learning model training. You have your training loss, you have your validation loss. At some point, you'll see that as you keep training your model, the loss keeps getting lower and lower and lower and lower. But if you keep going and you basically have the model trained towards the very end and choose those parameters, then when you apply it on your test set, you'll see that your model does not do well because there's some sort of overfitting that is going on. So you have to make sure that you minimize overfitting as much as possible. By overfitting, what I mean is your model does well on the training set. You see that your training set accuracy will be 95%, 99%. As soon as you go to your validation set or your test set, you'll see that it's like 40, 50%, 70%, right? So which means that your model is overfitted to your training set. And then you have your test set. The test set evaluation is done only after the model is fully frozen. Yes, so if the model performs well on training, test, and validation, it is likely to generalize. If it performs well only on the training set and doesn't perform well on the test set, it could imply some overfitting. So the machine learning pipeline, to summarize, you have data ingestion. You split the data, like I said, into your train validation test set. Before that, you'll have to have the data preparation. You have model training. You decide your model, train your model, validate your model, evaluate it. After you have evaluated it, you test the model, and then you register and deploy the model. And obviously, there's a stage of monitoring and feedback. You have to get continuous feedback from the clinicians once the model has been deployed. And based on that, you can always refresh or retrain your model. Okay, so now what are the different modalities of data? So like we have seen over the past 2-3 days. So just summarizing that, you can have personal demographic data, you can have imaging data, pathology data, omics data, transcriptomics data like we saw yesterday, and also EHR and clinical data. So we haven't covered that. I'm sure many of you here are working on that. So when, let's say, patients are admitted to the clinic, you have their vitals that are measured, right? Their blood pressure or their heart rate and other kinds of vitals. When you take the blood work, you'll have many different parameters. So a lot of these data, or most of this data, is entered to the health records. So if available, you should take this data into account as well while training your model. So once you have integrated the data sets, so these are the different tasks, or the typical tasks. You can have many more tasks. Segmentation of the detection, segmentation, classification of the disease, survival prediction. Sorry, there's a typo here. And then you can have longitudinal disease tracking as well. So by longitudinal disease tracking, what I mean is that, and we saw a few examples, how is the disease progressing? So is the patient getting better? Is the patient getting worse? Is the treatment working? Is the treatment not working? So these are typically the kinds of applications. And then orchestration. So this is important because after the model is run on the inference set or on the new data set, on the test set, how do you provide the results to the clinicians? Right? So we haven't discussed that in detail. I mean, yes, we discussed the interpretability aspect where we saw the gecko outputs, and I showed how it can be made more explainable. But clinicians, or let's say radiologists, pathologists, they are sort of they are individuals who like to see images. So how do you present to them these results? So typically, when it comes to using these images, ingesting these images and pushing the outputs, so you have something called the PACS system, Picture Archiving and Communication System. Okay, so all the radiologist or the radiology systems, when the images are collected using these scanners, they are saved in the PACS system. The PACS system has the functionality to display the image and to annotate the image. So because this is something that the clinician sees, they don't have Slicer installed on their machine. They don't have ITK Snap, right? So these are all research software. They have more clinically focused software within the PACS system. Okay. Now the PACS system can have multiple components. So one of the components is the clinical PACS that they use to actually visualize the images. They can rotate, they can pan, zoom, crop, do multiple different things, annotate. But then there's a research PACS also, because as researchers, we won't have access to the actual PACS system because that is what they use to make their decisions. The hospital will make sure that the research, the clinical PACS is available only to the clinicians who are involved in decision making. But we as researchers, we want to see if we can visualize some of these images, push our results. So what the IT system does is they create a research PACS. Now this research PACS is more important for us as model developers because once we develop our model, and first of all we have to do some sort of validation, some sort of evaluation on the hospital data set, right? In order to do that, we want to test our model and push the results back to the doctor. Now we cannot push it back to the clinical PACS. That's not allowed. We push it back to the research PACS. Now they can log in to the research PACS and they can see how our model has performed. Okay, so research PACS is something that developers or researchers have access to. And a lot of times, because of telemedicine, the doctors might not be around at the desk. They still want to be able to make decisions. So you have phone apps where you can communicate or you can send these results to. They can look at it on the phone. And web link. By web link, what I mean is you provide them a link. When they click the link, it will take them to a sort of a PACS system, but that is hosted on the cloud. Right? So these are different ways in which clinicians can interact with the decisions that a model spits out. Okay. So coming back to multimodal AI again, you have radiology images where you have X-rays, MRIs, PET scan and so on, pathology slides, you have different kinds of imaging reports, genomic data, and genomic data can include different kinds of mutations, MGMT, EGFR status, TERT mutation, and so on. And then clinical data, like I said, you can have different labs, vitals, demographics, and so on. So put together, we can develop these true multimodal predictors of disease diagnosis, prognosis, and treatment response assessment. So this was one of the first papers that came out when it that dealt with classifying the ImageNet dataset with deep convolutional neural networks. And then this is the paper that sort of changed the paradigm, and nowadays it's mostly about transformers. And the underlying, let's say, theory or the concept there is attention. By attention, what I mean is how does one part of your data relate to another part of the data, right? So that's the attention mechanism. So yesterday we saw one of our applications where we used LSTM. So nowadays we don't really use long short-term memory networks. We don't use LSTM anymore. It's mostly about transformers. And this is one of the papers that changed it all, the vision transformer paper, which says that an image is worth 16 cross 16 words. Okay, so why is AI in medicine different? First, access to data is uneven globally, right? So the kind of access that, let's say, people in Europe will be very different from the kind of access that people in Asia will have. Even in Asia, the kind of access that researchers in China will be very different to the kind of access that researchers in India will have. So a lot of that is dictated by the demographics of the population, what is the nature of the disease. For example, when I was a PhD student, I was working with that radiation necrosis recurrent tumor project. Some of the head and neck cancer data that we got was from a hospital in China. And we could not get that kind of data from hospitals in US because people in the US did not have that kind of cancer, right? So it depends on where that kind of cancer is more prevalent, okay? Affordability limits deployment in low middle income countries. So there are a lot of grants that, at least that in the US, where we have these grants where we can develop techniques that can be deployed in low middle income countries. And equity across populations is not guaranteed. There can be differences in population, this heterogeneity that we spoke about, and interpretability is essential to clinical trust. So not just in pathology that we discussed yesterday, but also in radiology, if a model makes mistakes, we need to know why the model is making a mistake, right? We need to tell the clinician what sort of data the model was trained on. During the training stage, what sort of mistakes that the model actually made. So these kinds of interpretability techniques are essential to garner clinical trust so that models can be deployed in the clinic. Medical expertise is also geographically imbalanced. It's not just data availability. So for a fact that I know that the number of pathologists available per 100 or per 1,000 patients in India is very different from the number of pathologists available for the same number of people in the US. For that matter, radiologists or other kinds of clinicians as well. And a lot of places you have more specialized clinicians. You will have, let's say, cardiothoracic radiologists. You will have breast radiologists. You will have, other radiologists with more specialized expertise. And in other places, you will just have general radiologists, where the same radiologist will have to read everything, right? So there is obviously difference in medical expertise also. It's not just data availability. It's important, and this is where the foundation models come in. These foundation models are trained in high resource settings. I mean, you'll see that most of the foundation models that have come out are probably from industry, right? From the Googles, from the Metas, and so on. Very few foundation models come out from academia. The reason is that they have, they have the money, they have the compute, right? So as academicians in academic institutes, we don't have, and it's very difficult to expect to have that kind of compute because of the money involved. That doesn't mean that we should stop doing research, right? Eventually, the people who developed these models in these companies came out of, there were people like you, right, who went from universities, who had more advanced degrees, PhD degrees. They went there and they trained these models. Sam Altman, he did not train models. The people who trained models were the ones who did the PhD and joined OpenAI, right? So, but having said that, high resource settings are mostly available in industry, so that's why you have these AI models, these foundation models coming out of there. But we have to ensure that the way we use these models, they have to be properly tuned to be applicable to settings that we have, in the local hospitals that you want to deploy your models. Deployment often occurs under distribution shift. So like I said, model trained on one distribution of data, when it encounters out of distribution data, it might not work. So there are techniques to account for this distribution shift that we should incorporate into our model making, into our model training. Dataset issues, we touched on this. Sometimes key predictors might be missing and there can be poor quality data. We have to make sure that the data is properly quality checked, and the poor quality data is either removed or somehow we modify that data to make it high quality. So this is very important. More data does not necessarily imply better data. So a lot of times you would think that, oh, I don't have enough data, that's why my model is not getting better. That's not the case. So yes, in an ideal world, if you get more and more data, your model training should get better and better. You should get better results. But usually, if you have, that's not the case. Or other way around. That's usually the case. But sometimes you'll see that if you have a lot more data, that doesn't necessarily mean that your model is getting better. That's because you would expect that the reason why a model should get better with more data is if you're introducing more variability into your training. If you include more data, but the nature of the data or the kind of, let's say, information that is there in that data is still same as what was there in the previous data set, you are not introducing any variability into model training. So why will the model learn something else, right? It will still learn what it has learned. It won't get marginally better. It might get a little better, but it won't get a lot better. AI cannot fix flawed data sets. So clinical data sets are small and heterogeneous, like we saw. Foundation models assume massive data availability, so that's why these models, are good, let's say, feature embedders. But this mismatch can lead to brittle systems, and that's why we have to do these fine-tuning, these active learning sort of applications or sort of settings. We have to deploy them in these settings so that they keep getting better. So coming back to our Gen AI, how the post-treatment image will change, how the lesion will change. Okay, so you see how this is how the pre-treatment was, and you see after the post-treatment, this is how it will look, and we predicted that, right? So these are other applications of Gen AI systems. Is there a question? No? Okay. So let's move on. So we can wrap this up in the next few minutes, and then we'll go to the QA session. So another application that we have been pursuing is, using proper conditions to generate images. I mean, yes, you can ask your GenAI model to take this image, take image A and generate image B, but we have seen that if we do that, a lot of times the image does not respect the geometry. It does not respect the topology of where the different constituents of the image are. Now, just to simplify that, the different parts of a brain. So, what are the different parts of a brain? Can you give that are observed on images?
Cerebrum, medulla.
Okay, but what are the different tissue structures? So these are the different components, but what are the different tissue structures? Like white matter. The generative model to generate synthetic images. If we did that, the quality of the generation improved a lot. So this is work still under review, but this is something that should be done. It's not just blindly applying generative AI or training Gen AI techniques. So this is the same project where we used anatomy guidance, and then once we train a model, we can use it as a feature extractor for multiple different downstream tasks. Okay, so something else. So yeah, foundation models, like I said, they're trained on imaging data, language data, other health data, and they can help us with all these different capabilities. So we just saw a few examples, but it can help in enhanced communication, better report generation. It can obviously help us advance diagnostic support, streamline workflows, and more importantly, discover population level insights. So you might be interested in not just what's happening to a given patient, you want to understand what's happening at a population level. So because foundation models have been trained on so much data set, they have a better capability of helping us understand what's happening at a population level. So this is again recent work that we have done in our lab. So we have seen that when we applied existing foundation models on different data sets, and this is in neuroradiology, we found that these models don't really do well. One of the problems that we observed was indeed the distribution shift. Like they don't take into account the distribution shift. So what Moinak did was he incorporated this distributionally robust loss function that helped us encounter this distributional shift between the different data sets. So maybe we can pass the mic to Moinak and he can quickly explain what this DRO loss is.
So am I audible?
Yeah.
So when you train a deep learning model, what happens is it tries to overfit. Yesterday we saw the example, right? The adenocarcinoma and squamous cell carcinoma. So the number of patients in squamous cell carcinoma was much larger than adenocarcinoma, and the model kind of fitted there. So when we train a foundation model, we take the data set from all the available institutions that we have. So let's say institution A has, let's say, like a large number of patients, and all the other institutions have smaller cohort size.
Just walk over here so that the mic can focus, the camera can focus.
Sorry.
Yeah, sorry.
Yeah, so yeah, as I was saying, like the model might learn the data only from the institution which has the largest number of patients. But like it's bad that we are ignoring the other institutions or the other patients. So what to do? So that is where I designed this distributionally robust optimization loss. The distributionally robust optimization loss. So what it does is very simple. So we have different distributions like institution A, institution B, institution C. You can consider them as different statistical distributions. And rather than training the loss, which is minimizing the loss function on all the cohorts combined, you just weight more on, or you just ask the model to learn more on the cohorts which have lesser patients, and like kind of a bit weighted less on the patients which have larger patients. So in turn what happens is you give equal weightage to all the different distributions, all the different patients. And so that is one thing, like focusing on different institutions, but there can be another angle to it. So for example, maybe most of the patients, like for brain tumors, like let's say most of the patients might have primary brain tumors, which is glioblastoma or gliomas. And there can be very limited set of patients who have metastasis or who have meningioma. And now you train a foundation model without the group DRO loss, the model will always predict it, like, whatever the prediction it will make will overfit on gliomas. And it will perform very poorly on meningioma. So again, the group DRO loss kind of, distributes this training, and then your model is kind of performing robustly on different types of tumors across different cohorts.
Okay, so yeah, so we can send you the link to the paper. You can always read up on how we implemented this. So what did we do after that? So we wanted to use this foundation model that we trained and to do prediction, to perform prediction on the different kinds of molecular markers. So we had the list of molecular markers that you see here, the ATRX, P53, TERT mutation, P10 mutation. So all of these kinds are markers are very important for eventual treatment of the brain tumor patients. So we use this foundational model to predict the different markers that were present. And these are some of our results. So for the most part, we saw that, so these were some of the existing methods, DINO, BYOL. When we included the DRO loss, the distributionally robust loss, our performance actually increased. So what this shows is that we can account for this distribution shift in the training itself. So if we do that, our model keeps getting better and better. Yes.
Sir, you told about the quality of the data.
Yeah.
So while we are applying the DRO loss, so maybe we are getting 150 samples of glioma and 50 samples of meningioma, what sir told. So let the data of the glioma cells, while it is 50 only, but the data quality is much more better than those 150 cells of meningioma. So in that case, how DRO loss is going to affect?
So here, so what we did here was assuming that once we did the pre-processing, the data quality wasn't an issue. So we had similar data quality because we performed pre-processing, we registered it to an atlas and did the skull stripping and whatever pre-processing in the same way for all the patients. So this DRO loss is specifically to take into account the, this class imbalance, right? So you have fewer number of, let's say, samples for one data set, more number of samples for another data set. How do we provide different weights to what we are learning from the lower represented class versus the higher represented class? So that's all that DRO loss does. It does nothing to improve the quality of the image. Okay.
Thank you, sir.
Yeah. So next, even though foundation models are great, these task-specific AI models aren't really going away. So if you have a specific task, a very niche task, by all means, if you have a simple enough method, an elegant method that you can train to solve that task, go for it. Just because you have foundation models doesn't mean you should use foundation models. Okay. But having said that, if you think that foundation models are giving you good representations, you can go ahead, fine-tune these foundation models for your task as well. So key point, these general models, these foundation models have broad capability because you can fine-tune them with on your data set that have fewer labels and they can be scaled across modalities. Task-specific models have high precision for well-defined problems, but they do not really translate well if you take another data. So let's say that you have trained a model on Apollo Hospital here, and if you're happy with the model and if you have the same kind of, let's say, patient distribution or data set distribution coming in, by all means you can work with that model. But it's almost impractical to expect that the model that you have trained on this data set will work on some other data set, right? So if that's the case, you are better off using a foundation model or, let's say, retraining, fine-tuning your data. So the future of radiology AI or pathology AI is not either or, it's hybrid, and at times it's workflow independent. So there's this new concept that has been catching everyone's attention. It's called digital twin. So by digital twin, what we mean is, so you have the patients, so we create a digital version of the patient, a digital twin of the patient. So what that means is, when you have a patient, you can give for a particular condition, you can give them a drug, you can give them some treatment, and the treatment works in a certain way. Now ideally what we would want to get to, like for personalized treatment, for precision medicine, is we want to be able to know what if you give treatment A, what will happen to the patient? If you give treatment B, what will happen to the patient? If you give a combination of A and B, what will happen, right? So there can be, many different permutations and combinations, and it's difficult to actually have enough patients with all these different kinds of settings to train a model. So which means if we can train a digital version, like if we can train a twin of the patient, then we can turn certain knobs, and the doctor can then say, okay, if you give treatment X plus treatment Y, then this is how the patient will respond. If you give just treatment X, this is how the patient will respond. So we should give a combination of treatments, right? So that's the idea behind digital twins. So however, to train good digital twins, to train high fidelity digital twins, we need to have multimodal data, because usually for the most part treatment decisions are based on multimodal data. They don't just look at the images and say if the patient will respond or not, right? So now if the patient has a certain disease and if the patient is really old, for example, then the doctors will know if the patient can tolerate that treatment or not, right? Sometimes you'll see, and I'm sure you would know of cases where, because the patient is old, the doctors say, okay, let's not treat that patient because they cannot really tolerate this patient. We just manage them in a way that can make their life better, that can prolong survival. As opposed to, if there's a younger patient who we know could possibly tolerate that treatment better, then they would give that treatment to them, right? So this is not just, looking at the patient's image and giving a treatment. You consider all these other factors. You consider comorbidities. For example, let's say, and this is something that happened to a relative of mine, they had diabetes, right? And because of diabetes, they had to wait to actually treat them in a certain way, right? They have to give them some medicines so that, that's under control before treating them, right? So, and sometimes patients are on blood thinners, right? If they are on blood thinners, a lot of times while doing surgery, something wrong might happen. So you have to take them off those drugs and then give the treatment to them. So inherently, treatment is multimodal. And what digital twin can do is it can help us simulate that multimodal scenario. Okay, so what we have done is, in the context of brain cancer, we want to predict if there's response or non-response and how the patient will respond. And what we are doing is we are collecting different kinds of data, such as, I'll show you what we have done here. We have, in the context of brain tumors, you can have surgery, you can have radiation therapy, you can have chemotherapy, and also it's not just that. For the training data set, we have the days to treatment. After surgery, how many days elapsed before the first treatment was given. After that, how many days to the second treatment. So you have this time information as well. It's not just the image information. So you can take all of this and you can develop your partial differential equation and combine them with deep learning models to predict how the tumor size will increase or decrease due to different treatments. So that's what we did here. And we found that, I won't really go into details of this, you can always look that up in the paper that's currently on archive. So we saw that here we wanted to predict how the disease, how the treatment will affect the disease, and DSC stands for dissimilarity coefficient. We see for the different methods, for UNET, for Cornwell STM, for a neural OD method and ours, how the predicted size change was different. So that's what we saw in this particular project. So this is still very new. We are still working on this. There are multiple groups that are doing this, but eventually we would want to get to a point where we can use the different kinds of treatment options that are there, different kinds of, let's say, modalities of data that are available, and train a digital twin that can help the doctor, provide some information as to what if scenarios, right? So that's what we want to tell them. Yeah. Cool. So yeah, so let's stop here for a short break. So it's 11:35. So let's reconvene at 11:50. And yeah. So by the way, if there are any questions, we can take questions. Sorry.
Yeah, so for digital twin, what kind of data we would need? Because what it seems that if we want to maybe create digital twin, the property of all the data, that basically the features that we collected, that should also evolve as the patient would evolve.
What does that mean? So evolve as the patient would evolve?
Like, imagine, let's say, for a 10-year-old patient, we collected some attributes or some features.
Okay.
And if we are talking about the digital twin, maybe 5 years down the line, the properties might change.
What properties?
Like in terms of the shape and all, right? So, for example,
Yes. So you're saying that, okay, so you're saying that, the way the image looks now will be different from the way the image looks 5 years down the line?
Yes.
Okay.
So what I'm saying is, in order to create such models,
You will need sequential data.
Yes.
Yes, so you will need, so digital twin is inherently temporal, right? So you have imaging data not just from today, but ideally you would want imaging data from today, from the first treatment, second treatment, 1 year down the line, 2 years down the line. And it's not just imaging data. You should have the corresponding clinical data or EHR data, reports data also on the multiple time points, because you're right, because of how, the human body ages, right? So obviously the image will also change. Because of treatment, the image will change further. The kinds of other data that we obtain will change. So yes, unless you have this temporal data, you cannot really train a digital twin. Yeah. It's not just getting a data today and predicting what will happen tomorrow. That's not something clinicians will believe in.
And then at least the settings like India, here what happens, a patient gets treated at different hospitals, and the drugs that they get introduced to, that may have different effects.
Yes.
So my digital twin might get outdated than what we could have earlier.
So you are right, different patients can get treated at different places. Sometimes the data may not be available, and obviously because of these different variations, it's difficult to control how these models can be trained. But having said that, if there is enough data with these variability, if there's enough data with patients treated at different hospitals, it's the same concept as a foundation model. Eventually, if your model sees enough variability, you would expect that it has learned something, right? And yes, you have different kinds of chemo treatment. You have different radiation treatment, it's not different kinds, there are a few kinds, but let's say newer and newer drugs are coming out, right? So that's why you're saying that digital twins can get outdated, right? But what we can do is, we can always retrain these models with the newer data and still keep what was happening with the old data, because the older version of the digital twin has still seen some biology, right? So fundamentally, there is something that would still be common between what happened to X group of patients 5 years ago and what will happen to the new group of patients with new kinds of treatment, right? We don't want to lose that information. We can always fine tune our model with newer information, but hopefully with the models we are training, we can retain some of the old information, so that that can help in understanding response to tumors, right? Yeah. Response to treatments.
I get it. I mean, on the other angle, if we see this digital twin, the data itself is very, very critical,
yes.
right? I mean, so there has to be maybe a common governance around this,
yes.
that will kind of secure or maybe mask such data, so that our PII is still there. Basically, the PHI is still denonymized, I would say.
Yes. So yeah, obviously, you have to do all these things. There'll be PHI information, so you have to anonymize all of this. But you're correct that these data sets. So again, digital twins, it's still very early days. There are not enough data sets that we have to train digital twins. In fact, one of our efforts in our lab is to create this synthetic data to train digital twins. But eventually there has to be some governance, not just from the privacy preserving perspective, but also creating these benchmarks, where we start to create these data sets that people can train their digital twins on. Nothing like this exists currently.
Okay. And sir, also I have question around a lot of the papers that we have gone through since last 4 days. It looks like more of a small task that will get done out of these. Do we have set of kind of agentic like framework where we'll have sequential, right, combine these tasks in a pipeline, and that will help the clinicians or
right.
radiologists?
Yeah, very good point. So what you're trying to say is that the works that we have reviewed so far, they are for very specific tasks. So what if you had your data set and you had a model an AI agent that could take that model and automatically decide what sorts of, let's say, pipelines could be applied, pre-processing, AI models, what sort of parameters, and then decide, what could be done to, and what are the different tasks that could be done, right? So it's almost like an automatic, let's say, scientist or something, right? Yeah. So nowadays there's a lot of work that's being focused on this part. So in pathology, I know there are a few groups in Europe that are starting to develop these agentic AI systems, but still very early days. I think this digital twin can clearly fall under the umbrella of agentic AI, right? Because you have your data and then you basically try to train an AI agent to come up with different possibilities, right? So that's what you're trying to ask here, right?
Yeah, because agentic AI in the normal basically image processing has gone way beyond right now. So it's like a normal, we give the normal prompt and we get a lot of things done right in image or video form. But what I felt, I'm not sure, maybe you would be the right person to answer, like how far we have gone in terms of
not far at all. Not far at all. I mean, I think it's still very early days.
And how many of the whatever we talked about, how many of these are already live in hospitals?
So that's the thing, right? So what is live in hospitals is actually the small tasks like detection, segmentation. Even report generation is not there in the hospital. They're still beginning to do that now. So digital twins applying, like actually translating to these hospitals is, we are probably 10-15 years away. Okay, so that's what I was trying to say. So when you look at the kind of the stage where we are with machine learning research, with CV research, computer vision research, we are at a very advanced stage. But when you look at what is there in the clinic, it's still at the very grassroots, right? Even the most fundamental problems are still unsolved. So yeah, I think we are ways off from actually seeing an agentic AI live in action in the clinic.
So I mean, as an expert, what's your
what needs to be done?
Yeah.
So what needs to be done is, like I said, you have to have enough systems. So if just from the point of digital twins, we have to have enough systems that are actually trained, that have been trained to build trust, and then also, like you said, with a lot of these new treatments coming up, we have to see how digital twins can be adapted to these new treatments. So these things need to be done before we can even see any of these digital twins in action.
Okay, I mean, I'm not asking about the digital twin, more
so just agentic AI systems, right? So it doesn't have to be digital twins, even agentic AI systems. So we need to know what the eventual applications are. So here's the thing, and we'll see some of that in the next few slides in the second half of the lecture. It's not just about predicting or predicting a disease or detecting a disease. Eventually we would want to know, or if a model has to be used in the clinic, there has to be certain value that the clinic will get out of it, right? It has to get some cost savings, first of all, because all hospitals are eventually, what they will care about is the revenue, correct? Yes, you can deploy AI systems, you can deploy agentic AI systems, but does it improve the clinical output? Does it improve the revenue, right? What is the return on investment? So these are actually the more important things that will dictate whether or when and whether these systems will actually make their way into the clinic.
I think what I feel from the medical side is like there are two bodies, one who is developing these systems and another is the hospitals themselves.
Yeah.
Right. So I'm not sure how far they are able to kind of overlap each other to kind of bring in these systems.
I mean, slowly we are getting there. Slowly we are getting there. It's not a change that will happen overnight, and that's why we are writing these papers. That's why we are continuing to do the research that we are doing. So eventually, we are getting to the stage where we are sort of collaborating, and things are slowly making their way into the clinic. But like I said, very early days. Hopefully, eventually it will happen sometime soon.
Thank you so much.
Yeah, thanks.
Hi, sir.
Yeah.
Sir, your insights on clinical considerations for AI deployment was very helpful. So I have questions on bias.
Bias, okay.
Yeah. If AI models are being trained on data sets from specific population, how do we prevent the predictions were the populations is from diverse groups.
So same concept applies. Either you start training population specific models, like you have different models for different populations, so you can do that, or you start to fine tune your models. You train it on one population and take limited examples from the second population, and you start to fine tune those models. That's how you can do it.
Thank you.
Okay, so no more questions, I believe. So let's then take a 15-minute break and we reconvene at noon. Okay, so we'll have the final session from 12 to maybe 12:30, 12:45, and after that we'll break for lunch. Okay, thanks.
Okay, before you leave, people who are accommodated in the hostel, the lunch hours, please follow the Chief Warden office.
Okay, welcome back. So this will be lecture 8, where we'll continue our discussions on the clinical considerations for AI model deployment. So this will be the part 2 of the lecture. So what we saw in the previous few slides was that for the first half of today's lecture was what are the different factors that we need to consider when deploying the model in clinic. And let's say that you have different kinds of AI models that have been trained. What's next, right? So first, how do we pick a model for clinical use? Which vendor? Now this is important because if you remember, we discussed that for a particular solution, so let's say that you're working on detection of lung cancer, of lung nodules. And this is well researched problem, which means there are multiple vendors that can provide you or that do provide you solutions for the same problem, right? I mean, similar to what goes on here. So if there's an equipment you have to order, I'm sure there's some sort of process where you invite some bids, some tenders, right? And then the institute will have some policy to decide which vendor to go with. So along similar lines, if there are multiple different vendors, how does a clinic choose which vendor to go with? Who is going to use it? So that is also very important, right? So who the eventual end user will be? What are the metrics of success? And more importantly, what are the post-deployment considerations? So once the model has been deployed, what are the different aspects, what are the different factors that we have to consider for making sure that the model keeps getting used for that particular task? So yes, eventually we want a product because the product is what will be used in the clinic, but what the hospitals look for is not a product. They look for a partner, because just the way AI models are being developed and they are being deployed in the clinic, it's not like we get the model, we deploy it in a hospital and forget about it. It's a partnership. It's a two-way street, right? So if you see, a lot of times what happens is when you approach, or when a vendor approaches the clinic saying that a hospital saying that yes, we have a solution, it's a wonderful solution, they will show a demo, and that demo will work amazingly well, right? And it's like, okay, this is like the next best thing, like I want to get this to my clinic right away. But we should not get carried away by that. So if you are, let's say, and it's not like every one of you will do co-research or get into machine learning, but you might end up in, let's say, some sort of a department that's actually involved in purchasing decisions, right? So you will have that AI expertise, you will know what goes into this model training and testing, but eventually, let's say that you complete your management degrees or whatever, and you do end up in these different enterprises where you deal with purchasing of AI systems. Now, you should understand, and this is very critical, that especially in the healthcare domain, if a demo works, that doesn't mean that it will work all the time in the clinic. And in fact, it's not just healthcare domain. So that's why if you look at self-driving cars, there have been, the different systems have been slowly developed over the years, and now finally you have these self-driving cars that are, sort of out there in the market. Still in India, it's still, you don't really have. I mean, I know that a couple of Teslas are currently making their way into the Indian market. I think Rohit Sharma just purchased one a couple months ago. I saw on the news, but the self-driving capabilities, the autopilot capabilities of Tesla still doesn't work well on Indian roads, right? Because it's not optimized for that. So we need to know that, what sort of data sets these models are optimized for. Defines clear ROI, return on investment, not region of interest, return on investment. So you have to define clear return on investment, and you have to align. So it has to be aligned with incentives across the stakeholders. And by stakeholders, I mean when it comes to a hospital, you have so many different stakeholders. You have the clinicians, you have the patients, you have the insurance, insurance agencies, right? So because eventually, when the treatments are done, patients will get reimbursed, hospitals will get reimbursed, and so on, right? So how does it align with the incentives across the different stakeholders? Improves continuously using data, feedback, and scientific rigor, right? So there was a question raised where one of you asked, what is there a facility where data can be fed back from the hospital to the system to improve their model training? This should be taken into account. So before you deploy, or before you consider deploying an AI system in the clinic, you should ask the vendors, can our system, like can our hospitals, can our doctors actually give you some of the cases to improve the model training in case the model is not working well, or if we identify some of the cases where our model does not work well, right? So you have to be very careful as to if the models will let you incorporate their data for training and how that can be done, and that's when the legalities come in. And scientific rigor, right? So they should be open to the idea that if the model does not work well for certain cases, they have to be open to the idea that, okay, now it doesn't work well, let's change it, or if at some point can we stop using the software? So there are different ways of licensing. There's this exclusive licensing, non-exclusive licensing, many of these different things. We won't get into the details of that. But you have to be careful in which, like, do you sign a multi-year partnership or do you sign a single-year partnership? Like, how do you do that, right? So you have to somehow de-risk it, because eventually ROI is what matters. So the vendors, they have to understand the radiologist workflow. So they have to engage with the RAD users. It's not like, yes, we have a system, we give you the output, and you visualize the output on your system. They have to know, the vendors have to know how to integrate with the PACS system, right? So that is very critical, and that's one of the things that we as academic researchers, we don't really have a clear idea about how we can do that. That is why we work with people who understand the PACS system, who understand the clinical PACS and research PACS. You work with the hospital IT to see how this can be done. Efficient with the regulatory clearance process, right? So you have to, so when you are in the discussion stage with the vendors, you have to talk to them regarding where they are with their FDA approval, right? First of all, it also depends on what sort of approval it needs. FDA has different classes of device depending on how it eventually leads to treatment management. There's class 1, class 2, class 3. There are different pathways like 510K. There's a PMA pathway, so there are different kinds of pathways, and based on which these products are approved. So one common pathway is, so let's say that there's a product that already exists that does segmentation, and you have a new product that you have built that does that same segmentation. You tell the FDA that there's this product that already exists, I want to do something similar, right? So there's a precedent that already exists, so you don't have to go through that entire process again. Right? So a lot of regulatory aspects has to be taken care of. Now finally, you have to have a shared mission, values, and there should be a long-term vision. It's not just a product. Like eventually, like I said, it's a partnership that you have to develop with the company. So how to evaluate AI clinical performance? You look at performance statistics. If it's segmentation, you look at dice codes, dice similarity coefficients. You look at something called Hausdorff distance, different sort of overlap metrics. But more importantly, for clinicians, for a hospital, did the AI enhance detection and what time savings did it lead to, right? So if a doctor can do it in 5 seconds and your AI takes 1 hour, what's the use of having that system, right? So you need to have measures regarding time savings. I mean, return of investment, obviously. Return of investment is not something, let's say, return on is not something you can control as a researcher. When you are working for a team for your company will have people in the financial department who make these decisions, right? But you can control how much time it takes. Like you can try to make your system faster as an AI developer to control how much time it takes to essentially make that decision, right? So that you can do. That the financial experts, the financial department cannot do for you, right? So, but the hospitals will see if the system, once it's deployed, will result in any time saving. And something that is very important is, yes, your model takes, let's say, in the inference stage, if you want to detect or segment out tumor on a given case, it would take 10 seconds for your model to run. That does not mean that it will take 10 seconds from the time the image comes in to the time the doctor actually sees the output. It takes 10 seconds for the image, for the inference process to run on your system, right? But now you have to deploy the system on the cloud or on-prem depending on whatever resources they are. And not just that, there is additional time. The image has to come in from the PACS. So in your lab, you already have the images on your system, right? But there in the hospital, the image has to be pulled from the PACS. You have to do some pre-processing, and then you have to run your pipeline, and then you have to push it back to the PACS. So there's T1 plus T2 plus T3 plus T4 involved there. It's not just T2, which is the time that it takes to run the model on your computer, right? So you have to take into account all these different things. Is AI helpful in detecting cases that could be considered the wow cases? So what does that mean? So a lot of times what happens is there's this concept of incidental findings. So there what happens, so let's say that the doctor is reviewing an X-ray scan or a CT scan for a particular condition, but when they're reading that image, they will see that, oh, there's something else that needs immediate attention, right? So they're looking for disease A, but they eventually end up, yes, finding or not finding disease A, but they also end up finding disease B or finding some signals that can point to disease B. If your software can help the doctors do that, that's a good software, right? Because it can help you identify some incidental conditions. And identifying these incidental conditions, it's a big area of research. And a lot of this is actually done in the NLP domain, where once the reports, the pathology reports or the radiology reports are identified, what the NLP systems, what the AI systems would tell you is, yes, there is disease A, but looks like there is some finding that is reflective of disease B. So it should be immediately referred to the right doctor. A lot of times these incidental findings are missed. We do not want to do that. So remember we covered like these 1 or 2 slides on the dental AI where we were looking at small calcifications, and I told you how these calcifications could be indicative of cardiovascular risk. Now if dentists are not trained to even think that these calcifications could lead to some adverse cardiovascular outcome, why would they even care about it, right? So you also have to train the doctors that if you have certain findings, then please do another read and try to refer to the right expert to see if there's something else that might be there. Okay. Understand and categorize the false positives. So there can be different false positives. So your system should be able to identify what these are, should be able to categorize, and should be able to do a further downstream analysis. So if your system doesn't do that, if the system doesn't do that directly, it's fine. But at least their team, the company's team, the technical team should work with you. So you should tell them, you should have a facility where you can tell them that, these are the false positives that we are identifying. Could we do an analysis on that? right? Why are these the false positive? What's different between, or false negatives? What's different between these classifications or these conditions as compared to the true predictions that maybe caused the model to falsely classify it, right? So what's going there? Can we try to understand it, right? So yes, it's a research problem. Clinicians might not always have the time to sit with the technical personnel to discuss this, but at least if your company has a team like that, so let's say that you're going into a company, you become a CEO or a CTO of a company. One of the value additions, so you have another company which does exactly the same thing. So again, a lot of this is something that you will learn in a management class, but let's say that you are the CTO of a company, you can actually have a portfolio where you tell them that, yes, my system can give you X percentage of accuracy, X percentage of AUC or F1 score or whatever, but we are also willing to work with the doctors to understand what the false positives are, what the false negatives are. Now, as soon as the doctors hear this, they'll say, okay, you give us something else, right? It's not just the product you are giving us. Along with the product, you are giving us something that we can use to improve the product, or that can be helpful for research, that can be helpful for the general community, for the scientific community, right? So these are the kinds of things that they would want to know. Okay, so performance statistics. So these are some of the different metrics. So the number of cases analyzed, what size of the what is the data set size that the model was trained on, prevalence. So sometimes what happens is you have a lot of class imbalance. We'll cover that in the next slide. What's the sensitivity, which is the percentage of true positive cases correctly detected. What's the specificity, which is the number of true negatives that is correctly rejected. What is the positive predictive value, negative predictive value. So I won't really cover these. So you can easily go to Wikipedia, or you can add in. So these are very common machine learning metrics that are used to evaluate model performance. AUC, accuracy. Accuracy is very simple. What is the percentage of cases that was correctly classified out of the total number of cases, right? So these are some of the common performance statistics that are useful, and your model should try to report on each of this. So just reporting on accuracy is not correct. If there's a class imbalance, you go for balanced accuracy or a balanced AUC. You have like a macro F1 score. I think someone had this question, this weighted F1 score, macro F1 score. So try to convince to the best extent possible to the clinician that yes, you have evaluated on your model on all possible metrics that are necessary for that particular problem. So coming to that, prevalence is very, very important, and I'll tell you why. So by the way, why is accuracy not a good metric? Anyone? So what is accuracy? The number of correctly classified cases divided by the total number of cases, right? So why is accuracy not a good metric? Can we have a mic here, please?
If there is severe class imbalance, then there could be cases like, let's say 90% are class 1 and 10% is class B, and if you happen to say everything, if the model says everything is class 1, then you are getting it correct 90% of the times. Right,
good. So I'll go to a more extreme example. So let's say you had 100 cases, and the task is to detect a tumor, okay, and only one out of the 100 cases, only one is a tumor, and the 99 cases are not tumor or benign. Now your model, the model that you have trained, it calls all the cases as benign, okay, which means your model is how much accurate? 99%. But is that a good model? No, because you are missing that one tumor case which is more important for the doctor to find, right? Because if you miss that tumor case, you will not give the correct treatment that might end up being fatal for the patient. As opposed to, let's say that your model tells you that 90 of the 100 cases are benign and 10 cases are tumor, right? So what is the accuracy of this model if it calls the tumor case correctly? So what is the accuracy of the model? 91%, right? It calls the tumor case correctly also. So right, so it's a 91. The model is 91% correct, but it is possibly a better model than the 99% model because you are getting that tumor correctly. Yes, there is a risk of over treating 9 of the benign cases, which can have adverse effects, hopefully not that adverse, it depends on the situation, obviously depends on the case, but at least you are getting that one tumor case correctly, right. So that is why prevalence, class imbalance, all of these things matter. Potentially they don't matter for probably they don't matter for a cats versus dogs problem, right. So that is why, healthcare AI, medical AI is very different, it's a very different beast compared to the other AI systems that are out there. It also matters for self-driving cars, by the way. Yeah. So I don't know if you heard this news. It was, I think, 3 days ago. Somewhere in California, these Waymo cars, self-driving cars. There was a power outage. Okay, so the entire city had a power outage, and the cars just stopped where they were. So it was a mess. Like the cars didn't really know what to do. So it was a mess. Okay, so these are actually some of the corner cases. I don't know what really happened there, but I'm sure the engineers would have anticipated a scenario where there will be power outage, right? Some sort of, let's say, adversarial attacks, some sort of attacks that might happen to the power system. It will go out. Yeah, so these are the kinds of things that you have to be careful about when it comes to training these AI models. Okay. So yeah, so that covers prevalence. Let's go to some of the performance statistics. So clinicians, yes, AUCs are great, accuracies are great. Some of the performance metrics are great, but acceptance, trust is probably more important than that. So you need to get radiologists' buy-in. You need to get that level of engagement from radiologists for a model to say that the model is good or not. Right. So for example, let's say that you have a model here that is 99% accurate, but none of the radiologists are using it, but you have a model that is 95% accurate, and you can tell VCs, you can tell funders, the different funding agencies that already 10 hospitals are using it, you will get more money. They won't get money, right? Because you already have buy-in from the radiologists. So here's sort of a one sheet, and there are different criteria that could be added to this, but these are some of the criteria that could be used for, let's say, deciding how good a product is. Should we go for this product or not? Should we buy from this vendor or not? And you can go through this. Maybe I'll touch on a few things. Let's say engineering capability, right? So you would obviously go with a company that is proven has scalable engineering organization, as opposed to a company that is maybe outsourcing its functionalities to some other team, right? There are a lot of consultancies which do work on medical projects, but a lot of doctors might not like it. So if the company has their own in-house team that works on it, that's always better than if that company is outsourcing some of the technical functionalities for a particular product, right? Integration experience. So like I said, there are so many startups that are coming up. I was at RSNA, like I told you a few weeks ago. The startup, the vendor floor was filled. It was full with startups. Like we had at least a couple hundred startups there, and they were doing all new things. But if you spoke to them, you immediately find out that not many of them actually had systems that could integrate with PACS, right? Not everyone thinks it through. Okay, we have a new product. Let's quickly get it out. Okay, let's start to make a big deal about it. Let's start to make a noise about it. But you should understand that it's not just getting the product ready. You should know how to integrate with PACS. If you don't know, identify partners who can help you integrate with PACS. Right. So what else? Security. So if your product already takes into account patient security, privacy, that's a much better product as compared to a product that does not take that into account. Yeah, so what are the other things? Medical standards, right? So sometimes what happens is, it's usually not the case. If there is a company, they would know what the medical standards are, so they would store their images in the right standard. But sometimes you don't really have all the functionalities, right? They will just have the basic import-export functionalities. other products will have other functionalities which let you not just import and export, but play around with the data, convert it into multiple different formats. So we saw with some of the examples that you tried out in the hands-on session, you had nifty formats, right? You can have DICOM formats. You can also save the image as PNG or JPEG. Don't do that. So you have these native imaging formats. If a vendor supports these multiple imaging formats, that's a much more flexible, let's say, software as compared to another vendor that provides a format that provides a software that only takes into account one format, right? So those are also the things that you should consider while deciding whether to go with a particular vendor, a particular software or not. Those are the technical evaluation strategies. So it's not just about a cool AI model, it's also about the time, right? So does it result in any time savings? So this was a simple study that we did a year ago, where we were looking at the efficiency of an attention-based deep learning network for identifying pulmonary embolism in CT scans. So yes, we had this attention-based mechanism that we used for identifying if the CT images had pulmonary embolism or not, but the more important thing for us in this particular project was how much time savings it led to. Okay, so our system was called AID-PE. So on the y-axis you see the time taken, on the x-axis you see the study number. We had about 140, 150 studies, and these are time taken in seconds. So we clearly see that the time taken for our system to ingest the image and give you the output was about in the order of seconds, as compared to how much time it took for the image to actually come in and get the output from the radiologists, where it was in the order of minutes. Now this clearly shows time savings, like this is an order of time savings, right? So even if you look at this case which takes 10 minutes, 10 minutes is what, 600 seconds, and even if you take our model that takes 10 seconds or 7 seconds here, that's an order of magnitude change in how much time it takes. So these are the kinds of, let's say, evaluations that need to be done. It's not just accuracy, AUC, sensitivity, specificity, whatever. So you need to look at time savings. So I also discussed briefly about the wow cases. So in radiology you can have, so if you're looking for something else, an abdominal CT on a routine abdominal CT scan, you can have an unexpected finding, right? Sometimes you can have these metastasis regions somewhere where you're looking for something else, but you find metastatic cancer, right? So those are examples of incidental findings, or findings which the radiologist is not primarily looking for, but they find it. So the key point is AI, just to summarize, it's not just about more sensitivity. It can expand, it should expand what the radiologists notice and not just what they confirm. It's the balance that matters. So false positive. So there are different false positive buckets into which we can categorize the misclassifications. So what are they? So you can have anatomic mimics. So sometimes you can have hemorrhages. You can have artifacts that look like hemorrhages, but they're not hemorrhages. You can have technical artifacts. So because of patient motion, you see certain artifacts that occur in the image. In dental images, we have seen a lot of artifacts. You can have implants. So implants can be, whatever material they're made of. If they're metallic or something, they can interact with the electrical field around it, right? So that can create some artifacts. A lot of times, benign pathology is flagged as disease. So you can have some finding that was identified long ago. Now when doctors look at it, they might say that, okay, this looks like a new disease. That's not the case. You can have post-surgical or treated changes. So a lot of times what happens is, let's say in the context of brain tumors, right after treatment, right after surgery, you'll have a lot of movement of the brain tissue, right? So if you just take that image immediately and show it to a doctor without providing them context of when that image was taken, they'll be like, okay, I don't know what's going on. Maybe there's there's some disease here, something is happening, there's a lot of infiltration. But if you tell them that the surgery was done 2 days before, I mean, most likely they'll know it because they're trained to look at these images. But if you tell them that these images were, these patients were treated a day ago, 2 days ago, they'll be like, okay, these are some immediate treatment related changes. Or if you remember radiation necrosis, so radiation necrosis is a treatment related change, right? Because of radiation treatment, you have the cells dying. There is necrotic tissue which can mimic tumor on MRI scans, right? So out of distribution cases, so there might be contrast phase mismatch. There might be some scanners which are poor in quality. So this leads to out of distribution cases. Label disagreement. So we covered this in the last session. There, while you are collecting data, you can have disagreement between radiologists. They can have different interpretations. We need to arrive at consensus. Sometimes the interpretations will be correct, but the way they arrive at the decisions will be different. This is a very interesting machine learning problem, the reasoning aspect of it. And then obviously you can have false positives where AI flags but case is already read. So these nuisance false positives, right? So yeah. So post deployment considerations. So you outline the role of physicians when working with these AI tools. So you need to clearly define how medical professionals, clinicians will interact and leverage the AI system in practice. You need to have this human AI feedback loop. Ideally there should be a way to enable radiologists to flag incorrect or unsafe outputs and provide that data back to the vendor, to the machine learning engineers. Clinical and ethical oversight. Define the ownership where AI disagrees with radiologists. You need to monitor bias across different subgroups and reevaluate performance whenever protocols change. So a lot of times protocols can change. So if they do change, if there are new images that are obtained, you need to reevaluate the performance of the models. And detect post deployment distribution shift. So we spoke about distribution shift in detail. So need to monitor AI's performance after deployment in order to find out if any of the changes in the data patterns, there is new data being collected. So let's say that the hospital had a GE scanner, immediately they are moving to a Philips scanner. So completely it's a distribution shift. Does our model work on the cases obtained from the Philips scanner, right? So you need to detect this post deployment. You need to analyze the post deployment, the changes arising from the post deployment scenarios. So going from bottom up, you have the technical performance evaluation where you can have external validation. You do the robustness analysis. Then you have workflow and usability evaluation. How easy it is to use the product. I mean, you might have a great product, but what if you have a very complicated UI? Like it gets difficult for the doctor to figure out, okay, you click this, where do you click? You need to make their job easier as well. You need to have a very intuitive interface for them to work with. Like you can't ask them, yes, you have a model, I mean, just a very extreme scenario, you can't ask them to fire up the Linux terminal and run it, right? Now let's say, obviously you don't do that, you have a UI, that UI cannot be very complicated, it has to be very user friendly, right? Clinical effectiveness, so the diagnosis accuracy, patient outcomes, does it actually help improve patient outcomes? So one of the things that hospitals could also do is they will have a trial run, and based on that they try out the AI model and then they see what sort of let's say effectiveness arises out of it, right? So does it improve patient outcomes? If it does, after that trial run they actually go for a full subscription. That's what they do as well. And then compliance and accountability and bias assessment, we need to keep doing that. So here's a readiness checklist. For data infrastructure, you have scalability, processing, and you have to make sure that to the best extent possible your model is future ready. So will your data infrastructure, so it's not like you have the capability of ingesting 1,000 studies, but in the future if you are expecting an increase in workflow, what if you don't have that infrastructure, right? You have to make sure that you are future ready. In data governance, data quality management, a lot of these things are very important. And in data validation, you have to make sure that you do your proper data profiling, measurement, and so on. Okay, finally, the last slide here, what are the do's and don'ts? Do's: use real clinical workflows for model design if possible. At least once you have designed your model, try to have cases from your real clinical workflow to validate, to test your model. If possible, get data from multiple institutions, multiple scanners. Most likely the data sets that you are already working with would have been collected from multiple scanners. So when you do your analysis, see or try to investigate if there is performance difference across scanners, across institutions, and report that in your papers, in your reports. Include explainability when relevant. So a lot of times, explainability might not be relevant. For example, if it's a segmentation problem or a nuclei detection problem, doesn't really matter how your model makes its decision as long as your model does a good job. But if there is an explanation that can be provided, let's say with Gecko, right? So we can provide an explanation as to why the model arrived at a particular decision. If you can do that, then definitely include that. So that makes their jobs easier, and it also makes it more interesting. So plan deployment early. So if you're working on a project, and I was having this discussion over tea half an hour ago, if you know that you are working on a product or the project that eventually has the potential of becoming a product, right? If you're already collaborating with a clinician, start to think about deployment aspects early in the process rather than after you have published a paper. Because after you have done that, it almost would seem like you are going back to the drawing board and starting from page 0 rather. Then try to monitor post deployment shifts. What are the don'ts? Don't build models in isolation from the clinicians. If there is even the slightest chance that the model that you're working on, that the tools and techniques you are developing will someday help the clinicians, try to involve them in the conversations. Again, this is easier said than done, obviously, because it's difficult to find clinicians. It's difficult to find clinicians who would be interested in that research. But that's what research is about, right? You have to go out of your way to reach out to people, to reach out to clinicians who might be interested in your work. There will be failures along the way. You will probably reach out to 20 people, only 2 of them might respond, and only 1 of them might be interested. But keep doing that till you find that person, right? Who can help you out, who can at least give you some assurance that the model that you're working will help them, right? Otherwise, it just stays as a paper. Report only internal test accuracy. Don't do that. You have to report external accuracy as well. Don't expect radiologists to trust black boxes blindly. There will be times where you have to provide interpretation, you have to provide explanations. Be ready for that. Treat deployment as an afterthought. I mean, I think we covered that. You have to start thinking about deployment from the very early stages, and don't assume that the model stays accurate forever. The models, it's just the nature of data. It's just the nature of models. So think about yourself, right? Nowadays there are so many different diseases being discovered. I mean, you can argue that there's more tests being done nowadays, but the human body is changing, right? Over the years, it's just the nature of evolution. It's changing. Right, so everything changes. AI models also, they won't retain the same level of performance compared to what they were 10 years ago, right? So don't assume that the model stays accurate forever. The vendors have to keep improving their model with newer data, with more complicated data, with more heterogeneous data. Okay, let's end with questions, if any.
Yeah, so I have question around like how do we, so for example, let's say a hospital, we provided some solutions and how do we quantify the efficacy of that solution? I mean, what are the best practices around it?
So these are the things that we can ensure, right? So okay, so just to, let's say, give you an example of a couple best practices. So effectiveness of the solution. So one of the things is how does it help in improving the workflow, right? So by that, how can you quantify that? only one aspect is time, right? So how long does it take the model to make a decision, like make a decision from the point where the image or the data is ingested to the point where the output is given? How much time does it take versus how much time does it take for the clinician on the floor to do that? That is one way of assessing effectiveness. The second way is, so if it's let's say a costly test or a costly AI model, it will cost the hospital something, right? Can they get that money reimbursed by the insurance companies, right? So that's something that also has to be taken into account. Or if they are charging the patient, can the patient be reimbursed for whatever the cost is? So eventually the insurance has to pay for it, right? So that's one way. So that's one way of assessing effectiveness. So other ways would be, with the time that is saved, what is it that the radiologist can do in that additional time, right? If they're reading 10 cases now, with AI, do they read 15 cases? But if you think about that, that can also lead to physician burnout, right? So there has to be some balance. So these are the kinds of things, it's not simple. So these are some of the things that have to be considered. Yeah.
Thank you.
Sir, I want to add to your questions answer regarding that
sure.
effectiveness. So you talked about that one for effectiveness and all. So who is responsible if AI model misdiagnoses a patient? In that case, whether AI developer or the radiologist, who is responsible for
So
that?
that's an ongoing debate. So currently, and probably for the most part, the clinician will be responsible, because they are the ones who have to make the eventual decisions. They are the ones who will make decisions that will alter the course of treatment. But I think, I'm sure, with the current governance, there are discussions going on as to AI developers have to take some responsibilities, right? Everything cannot lie with the clinician. Otherwise, if that's the case, then they would never trust a model. They'll never be okay deploying it. So, but a lot of that actually comes from how much convincing that model is. Like, if the AI vendors are transparent with the doctors as to what the model was trained on, what was it validated on, if they can tell the doctor that these are the kinds of errors that the model can cause, then the doctors will obviously have more trust. So they will use that model knowing that the model can give them these errors, right? They'll be comfortable, as opposed to a model which is entirely black box, where they don't know, and then if the model causes an error, they have to take the responsibility, right? Because eventually, I think the way this field is moving, the doctors will have to take the responsibility for the most part. Yeah.
And I want to go back to the last day session, sir. Last one. What safeguards are needed to provide to prevent misinterpretations of the clinical?
Sorry, what was the question again?
Safeguards to prevent misinterpretations for interpretability and explainability.
So
for the generated outputs, generative outputs, Gen AI outputs.
Okay, so what are the steps that could be taken to prevent misinterpretations?
Misinterpretations.
So in what context? So when you, so first of all,
for generative AI outputs, sir, we have discussed last day.
Yeah. So one of the things. So first of all, Gen AI outputs, Gen AI models are not really being used in the clinic. Eventually, when they make their way into the clinic, what we have to do, some of it we had discussed previously. So these Gen AI models, one of the things that we have to do is the metrics that we use for evaluating how good the Gen AI models are, they have to be very domain specific. Okay, so if you remember, we discussed this FID score. We clearly, and the PSNR score, or some of the SSIM scores. So these are metrics that might be good for evaluating Gen AI models from a more, let's say, natural image perspective, or from non-medical data perspective. But as soon as you go to medical data, these metrics are not the best metrics. So one of the safeguards that we can have in place is evaluate the Gen AI outputs on metrics that make sense clinically, right? So one of the, not Gen AI, but if you look at the report generation project, you can look at scores like Blue scores, Rouge scores, Meteor scores, which just look at, how the, 4 words, 3 words, or whatever combination you take, if what you are predicting is the same as what was there in the ground truth report, but that's not the case, right? What if you had a not in the output, right? You would still have those words, but you have a not in the output, right? So which means the clinical efficacy becomes more important. So you have to design metrics that are more related or close to the domain rather than just taking metrics from general computer vision or NLP, right? So these kinds of metrics and safeguards could be in place.
Thank you.
Yeah. Okay, so I think yeah, let's break for lunch now. So I know that you need to do a few things that was discussed, but yeah, let's try to reconvene at what time? Should we say 2? No, 2:30 will start, but we have to be back by 2:15, right? Yeah, so 2:30 the lecture will start, but let's try to be back by 2:15ish. Yeah, so he'll confirm and tell you, okay? Thank you.
Okay, good afternoon everyone. So this is day 4, good, very good. Day 4 and second session. So it tells me you are all very receptive. Okay, so in this up to now, what sort of data have you seen? Medical imaging, some feedback. Can I have some mic please? What type of data have you looked at until now in all the lectures? Very simple question, right? Yeah, please.
Radiology data, then we looked at pathology data, and we also looked at some of the transcriptomics or genomics data.
So if you look at the radiology and pathology data, what type of data is it? These are all images, right? Dimensions. What about dimensions? 2-dimensional, 3-dimensional, at least 2-dimensional, right? So a lot of medical data is actually not 2-dimensional. It's actually 1-dimensional. So in today's session, we are going to look at 1-dimensional time series data. So for example, if you look at the ECG signal or the EEG signal, these are all 1-dimensional data. So when we say 1 dimension means x-axis time, y-axis voltage. So another thing I wanted to highlight, so first difference is the dimensionality of the data. So it's 1-dimensional data that we look at, and because we have a very diverse audience, I also wanted to highlight another point. So what is the difference between, so what do you mean by diagnosis actually? When we say diagnosis, disease diagnosis, or let us say here we have put the title as characterization, disease characterization, what comes to your mind What do you think? Yes, please. You feel free to talk, no worries. There is no right and wrong answer, it's just your ideation and discussion. Yeah, please. Yeah, just 1 minute.
I think diagnosis is like to detect the category of the disease or the type of the disease.
Okay, identifying
Yeah.
the disease, right? Yeah, please, next.
When we talk about diagnosis, we think that a disease has already happened. We are looking at the symptoms and we are trying to predict whether it is the same thing that we are thinking or not.
Correct. So, it is more of disease identification. So, generally, and what is therapeutics? Treatment. So, treatment happens after diagnosis. So, it is after you identify the disease, then you do treatment, right. There are certain diseases, for example, once you have done the diagnosis, doctor actually prescribes a certain dosage or medication for a fixed amount of time. Then you are expected that in majority of the cases, the patient will recover, right. And there are certain diseases in which these diseases are for lifelong, okay. So, in these diseases actually you require disease monitoring. So, that brings us to the point here. If you look at the title here over there, continuous monitoring. So, diseases which are for a longer period of time, they require monitoring, okay. So, we have moved on from diagnosis, now we are in the domain of therapeutics, and in therapeutics under certain diseases you require continuous monitoring, okay. So, it has been shown that if you do continuous monitoring of disease markers, it actually helps in improving the therapeutic outcome. So, you get better treatment outcomes. So, we will have a look at certain papers. So, in this like in this talk, so we will look at some very basic, we will start from very basics, we will look at little bit of history, present and the future, okay. So, we will cover everything more or less, okay. So, starting on, so if we go to the next slide, right. So, if we talk about monitoring, then we are actually talking about different kinds of biochemicals. Biochemicals are essentially biomarkers which are being used to monitor the condition of the patient, okay. So, there are different types of biomarkers. They have been divided into two parts mainly, vitals and biochemicals. So, there are two groups, okay. So, a recent paper actually which came out in Nature Electronics. So, they actually have divided these two the ways or different monitoring into two different parts. So, you can monitor vitals, you can monitor biomarkers. So, when you talk about vitals, you can see the typical vitals are ECG, heart rate, blood pressure, SpO2, respiration rate, EEG, basal body temperature, GSR, gait and tremor. So, these are actually more of you can say physiological, these actually, if you talk about, if somebody is here from electronics background, so these are more of like signals, or rather I should say these are some things which are we call them as biosignals, okay, biosignals. Then when we come to biochemicals, these are metabolites, protein, glucose for example is a biochemical or a biomarker, biochemical biomarker. And then we have different kinds of pH, hormones, stress markers, inflammatory markers. So, you can actually use these markers to continuously monitor the condition of the disease, okay. So, you can monitor via vitals or you can monitor via biochemicals, okay. Now, depending upon whether if you are building an application for continuous monitoring, depending upon the disease that you are monitoring, depending upon the target biomarker that you are monitoring, whether you are monitoring vitals or you are monitoring biochemicals, the approach will differ, okay. The design of the device will differ, the approach will differ, okay. So, in order to make so there are different ways. So, if you look at the figure on the right hand side, so over here, so if you look at the figure on the right hand side, now there are many different, so we have moved, so these are all, this is all pathology or which is happening inside the body, you can say as an engineer you can say inside, and this is something which is outside body, and outside body we are actually making devices to monitor the different biomarkers, okay. So, you have you can make products like this which is head and eyewear or earwear. So, these can be used to monitor EEG or EOG, electrooculogram. And then you have different types of sensor systems which we will use to monitor different biomarkers or different biochemicals. Okay. So, you can have a wearable sensor which is actually continuously monitoring your glucose levels. So, today I will show you a person who is wearing this glucose sensor, and I will show you the continuous glucose monitoring sensor also. So, in this you are actually getting, so without the patient having to measure himself or herself, you can actually keep on getting the glucose level continuously every 5 minutes or every 15 minutes. So, it happens automatically. And these, so not only glucose, you can also monitor lactate, cortisol is, so these are also other, so cortisol generally is used for stress. Okay. Lactate is a marker for aerobic or anaerobic respiration. So, if you are, let us say somebody is interested into exercise monitoring. So, there is a point, if you keep on exercising, you will switch, body switches from aerobic to anaerobic exercise. And let us say somebody is a sports person and they might want to monitor their anaerobic performance, then lactate is the marker. So, there are many different applications which are actually being used. So you have, so if you recap in your mind, you can think of diagnosis, then you have monitoring. So, not always you go through this pathway where it is diagnosis and so diagnosis, therapeutics, then within therapeutics you have monitoring. Okay. So, not always you may have to do this monitoring because of some disease, like I said, somebody is a sports person, they want to monitor their health, there is no disease, but they still want some sort of monitoring. They monitor their glucose lactate levels, they monitor their EMG activity to estimate how much stress is being put on their muscles. So, in this way of overall there is a drive to develop wearable sensors. So, there is a drive, overall there is a research need or there is a market need to develop wearable sensors for continuous monitoring. So, if you look at if you look in your own life, you must have done a blood test. So, blood test is called as a spot measurement. So, you measure it once, but continuous monitoring will do it continuously in the background, even if, you are not doing anything, but so there are sensors which are continuously monitoring it. So, these continuous monitoring, you might ask why it is necessary. There are certain evidence which shows that, I will show you some papers also, where it shows that if somebody is continuously monitoring, it is better than spot monitoring. Okay. Anyway, so these are different markers. So, you might ask, let us say sodium. So, in this table you can see there are different markers, sodium chloride, potassium, calcium, and a host of different markers, a list of different markers. In this table actually it is given what is the physiological range. Let us say you want to monitor in sweat. Sweat means non-invasive, you do not need to insert a needle inside it, from the sweat itself you can monitor. So, what is the typical physiological range in which you are expected, and this is the sensing modality. Okay. So, these are all electrochemical sensing modality. So, these are all electrochemical sensing modes. So, different markers will have different kinds of sensing modality. Okay. So, generally for glucose, lactate, the modality is chronoamperometry or amperometry. Okay. Similarly, depending upon the, so these are metallic ions. So, for these we go for square wave stripping voltammetry. So, different and for cortisol you can measure in your saliva also, cortisol you can measure in sweat also and in blood as well. So, they all actually work on EIS, electrochemical impedance spectroscopy. Okay. So, this is the sensing modality. So, if you look at the sensor, you have the body, let us say, so I think engineers are more familiar with this block diagrams. So, let us say we have the body, and these body, so inside the body we are producing all these different markers, okay, and all of these are biochemicals. So, we need a sensor to convert the chemical signal into an electrical signal. Okay. So, a sensor, essentially sensor or a transducer will convert this chemical into an electrical signal, and this electrical signal you can you can take into an electronics board or a PCB, and then you can actually send it to a computational device to produce results out of it. to, let us say, you can actually use this computational part. So, here you can actually introduce AI to do a large number of applications. So, you can use AI to monitor disease. So, you can use it to predict conditions of the disease. Let us say somebody is wearing a sensor and doctor has diagnosed that there is a risk of heart attack. So, the sensor can indicate or AI can predict, okay, in the next 1 hour or 2 hour heart attack might happen. So, you will take some preemptive action to prevent that. So, and all this, so when we talk about this electrical signal, so this actually is a time series data. Okay. So, it is a one dimensional time series data. Okay. So, there is a reason a lot of actually when we think about medical or health related AI, lot of AI effort has been devoted towards medical images, because in the olden days images, if you think of X-ray, so always you have an X-ray plate. Okay. So, these were the things that were recorded for a very long time. So, naturally people started working on this recorded data for a long time. So, there was no device at that time to record glucose continuously and store it somewhere, whereas images were being recorded for a long time. Let us say WSI, whole slide images, they used to store it in pathology labs. So, they were recorded for a very long time. So, that is why they had a massive amount of data. So, as soon as this AI revolution came in, or the data data science field came into fruition or became more and more popular, people started utilizing these recorded data. Okay. And that is why you can see a majority part of the effort in AI is actually diverted towards the imaging aspect. A small part of the effort is actually diverted towards this time series data in sensing and monitoring. Okay, let me ask you a question before we go into this slide. Let me ask you a question. It's not a trick question. I wanted to understand, like, what is your feeling about this? What do you think is the prevalence of diabetes in India? How much percentage? Prevalence means, if out of 100, how many people will have diabetes? Just your ideas. Huh? You can pass on the mic just for the sake of recording.
40 to 50% above the age of 50 age in class, no, sir. Okay. So, most of them are getting that diabetes. Okay. So, that is the age factor is also more.
Okay. Considering age, you are saying up to 1 in 2 person will have diabetes. Okay. Anyone else? Any other figures? Let us say. Okay.
On an average 10%, sir.
On an average 10%, without like going into age and
age factors.
Okay, good. Anything else? So, we will see what the data actually says. So, one thing is, we have some feeling that, okay, diabetes is rising. Why? Because in and around, in my family also, like, if you look around, you see at least one person who is diabetic, right? So, there is a feeling that the diabetes, there is the number of diabetes cases are rising. So, we will see how much it is actually, what the truth is. So, this is actually a survey which was carried out, funded by the ICMR. So, there is an agency called the Madras Diabetes Foundation. So, in collaboration with ICMR, so they conducted this study called as the ICMR India B17 study. Okay. So, this study actually it was done to estimate the prevalence of diabetes. Let us see what is the prevalence of diabetes. So, before going into the numbers, I just wanted to highlight this difference. So, if you look at the right hand side plot here, so this is the urban area and rural area, and in the urban area diabetes is more than 10%. It is more prevalent in the urban areas. Okay. Just some data to show you. Now, not only diabetes, there is a condition called as pre-diabetes. Okay. So, if somebody has pre-diabetes, that means if they do not take care, they are likely to develop diabetes. Okay. So, again here also we see that there is a difference between the urban and rural populations in India. Okay. So, you can see these are different prevalence levels. So, in the urban area it is almost, in many states it is more than 50%, 15%, 15, and in rural areas it is slightly less. Okay. So, if you look at the overall, what is the overall? So, the overall is diabetes prevalence according to this paper, this survey is around 11.4%. Okay. But if you look at the pre-diabetes, so this is what I am worried about. So if you look at the pre-diabetes, the prevalence is around 15.3%. Imagine the worst case scenario is if all the pre-diabetes becomes diabetes, then it is close to 26% or 27%. Okay, so it becomes almost like one in 3% or 30%. So this, for this reason, we need to figure out, and diabetes is not alone. So diabetes, if somebody has diabetes, the risk for other non-communicable diseases increases, whether it is kidney or heart, like cardiac or chronic kidney disease, CKD, all of this actually increases. And there are some doctors and some scientists who believe that it may also lead to increase in the prevalence of cancer as well. So all because this is a metabolic condition, so some doctors actually classify it more as a metabolic condition. Okay. Anyway, so since there is a problem here, the reason I put up these slides is to highlight that there is a problem which needs solving. Okay. So the effort is not only from the doctor's side, we as engineers or biotechnologists can also contribute towards this effort. So let us see how we can do it. Now diabetes is an interesting problem. Why? Because in diabetes it actually requires continuous monitoring. So diabetes is a long term condition. So if the person is diabetic for a period of time, then this condition does not become reversible, it stays on. So in order to lead a healthy lifestyle, it requires actually a continuous monitoring scenario. So you have to continuously monitor the glucose level, give the medication based on that, and there are a host of other things that you can monitor. But the problem here in India is that there is a very high patient volume, and there is also lack of awareness, health awareness. So people do not really, so in the early stages diabetes will not have any symptom. So people are not really bothered about it. And then the traditional method for treating diabetes is called as track, where you have to keep track of all these 5 things. Okay, physical activity, diet, weight, and medication, everything you have to incorporate together. So it's becoming little bit hard, or it's a pressure on the patient to actually deal with this condition, because all this continuous monitoring, it's actually very tough to some extent, especially if somebody is living in a rural area where they might be far away from healthcare professionals. So for them this actually is a problem. So with this, if we have continuous monitoring application, so we have to make this in such a way that it can be expanded to a large, it can be wearable, so patient can wear it easily, and it should be easily operatable, like patient should not have difficulty operating it. So even this spot glucose measurement, sometimes people are scared to prick their fingers as well. Okay, so that actually leads to lack of patient compliance. So you can prevent all this with the help of continuous monitoring. Okay, so if you develop some continuous monitoring devices, especially I can show you the CGM sensor, continuous glucose monitoring sensor. You do not need any finger prick for that, it does it automatically. Okay, and in your iPhone or in your whatever Android, you can actually get regular updates, what is your glucose level at what time, and in this way you can track your glucose level. Now so the vision actually is to shift. So I told you there is a burden of disease management. So if somebody is suffering from diabetes, there is a high chance that there is a burden of disease management. How to manage that disease, either on the patient or on the caregivers. Okay, so they have to continuously monitoring their glucose level, and if they are on insulin, then they have to monitor their glucose level, calculate the dosage of insulin, and then take the insulin, so manually. And so it's okay for, to some extent, if somebody is suffering from type, like if somebody is more mature, but in type 1 diabetes it's actually happening in kids, so it's very difficult for them. So it's their parents who are their primary caregivers. So in type 1 diabetes, because it happens very early in the in age, so that time the primary caregiver is the parent, and then they have to also give insulin to the student, to the child. So all of this actually becomes like a burden of disease management. So the vision actually is to shift this burden of disease management from patients to machines. Okay, so the goal is that we automate this process so that patients do not have to worry about it. Okay, so they do not have to worry about pricking their finger, calculating the glucose. It should happen actually, calculating the insulin, it should happen automatically. So that is the bigger vision of continuous monitoring, so that a person who is having a disease and person who is not having a disease, their lifestyle becomes similar. So the the lifestyle or the quality of life for a person who is having the disease should become as good as the lifestyle or way of life of a person without a disease. So, that is the vision actually which we are pursuing. So, if you take the case of type 1 diabetes, then you can see in the corner. So, this actually was mentioned by one of the vice presidents of Medtronic. Medtronic is a big medical device company. So, according to her, it is actually 180 decisions. According to their estimates, a person living with type 1 diabetes, they have to make 180 decisions a day, okay, in a single day 180 decisions on top of living life, in addition to life. Okay. So, this is a massive burden on the patient. So, the goal is to shift this burden of 180 decisions from patients to machines, and the AI revolution is actually enabling that to some extent. I will show you some cases today and you will see how it is helping. Right. So, moving on. So, we have to build devices which can automatically or autonomously monitor disease markers like biosensors, and then determine, these are few questions. Okay. So, if you are making devices for continuous monitoring, especially for continuous therapeutics, then you have to answer 3 questions. When, 2 questions, and how much. So, these are the 2 questions primarily that the AI has to actually answer. When means when to give the dosage and how much dose to give. So, these 2 questions it has to answer. Okay. In certain cases you might have a third question also, depending upon, let us say there are certain applications where you might have multiple injections. Let us say there is something called as the bio inspired artificial pancreas. So, in order to monitor our in order to check our glucose level, so in a normal individual there are 2 hormones which are acting. What are those to control the glucose level? Insulin and glucagon. So, generally, so if you have if you are building a device and the action of insulin and glucagon are reversed, okay. So, you can so it might be possible that if you are building an artificial pancreas system, you might go for bi-hormone systems, means 2 hormone systems where you have to inject insulin as well as glucagon. Okay. So, right now most of the artificial pancreas that are available in the market, they are single hormone systems. To reduce the complexity, they are mostly single hormone systems, they mostly deal with insulin. But if there might be some other disease or some other application where there might be multiple. So, in that case another question comes into play, which means which medicine to give. But in majority of the cases, closed loop devices, they answer these 2 questions. Closed loop medical devices, they answer 2 questions, when and how much. Okay. So, I introduce a term now, closed loop. Okay. So, we will see what is this closed loop very shortly. We will see why we call this closed loop, what it means, and in some cases it is actually overused also, but you will see essentially what it means. Now, so you have this marker. So, you have vitals, biochemicals or biomarkers together. Now, the goal is to move from the body. So, these biomarkers are present inside the body. How will the sensor sense it? Okay. So, there are 2 approaches. One is the minimally invasive approach, or we call it as the subdermal approach, where the needle is just, so you have the skin here, is the skin layer here, epidermis, and the needle is just penetrating the epidermis into the dermis. So, the depth is around 1 to 3 millimeters. Okay. So, this needle also I will show you, we have some samples here, microneedles. So, this is one approach, and the other approach is non-invasive. So, this is non-invasive. So, this is minimally invasive. The first approach is minimally invasive, and the second approach is non-invasive. So, both these approaches have their own advantages and disadvantages. Okay. So, in minimally invasive, this depth of the needle is around 1 to 3 millimeters, and non-invasive is there is no depth required, it is actually extracted. Okay. So, you can extract these markers through various means. You can extract this using electric field, you can extract it, you may not even extract it, you can use infrared spectroscopy, near infrared spectroscopy, NIR, to also detect. So, there are many different ways in which you can actually do non-invasive detection. Okay. Now, most of the sensors, that wearable sensors that you will be making, or if you want to make, then it would be either of these two. It would be either a minimally invasive solution or a non-invasive solution if you are making it for continuous monitoring. Okay. So, if you think of the glucometer is probably the most widely used biosensor. So, so the spot glucose monitoring, it's actually you are not monitoring continuously, you are doing spot monitoring. Okay, you take your blood once, you draw your blood once, capillary blood from the finger, and you take it once. But continuous monitoring means the device will be with the user, they will be wearing it all the time, whether they are sleeping or walking or running, they will be wearing it. So, for these application you can either go for a minimally invasive or a non-invasive approach. So, this non-invasive approach where you are using an electric field to extract the fluids, it is called as reverse iontophoresis. Reverse iontophoresis. Okay. Pardon my handwriting, but it is iontophoresis. So, we have it is called as reverse iontophoresis. Okay, reverse iontophoresis. And so what is the origin? What is the origin of these markers? How are we able to sense this? So, if you look closely at this figure over here, if you look closely at this figure has been drawn very nicely, and it actually shows that my microneedle is away from the blood capillaries. Okay. So, it is not touching the capillaries, it is away from the blood capillaries. So, that means any minimally invasive solution, ideally you do not want the sensor to actually touch blood. Okay. You do not want it. So, what happens if you touch blood? So, if you are drawing blood, in the blood there are white blood cells. There are white blood cells present in this space also. There might be white blood cells present in this space also, but the volume of the white blood cells that are present in blood is quite high. Okay. So, as soon as you do any continuous monitoring on the blood, these white blood cells will form, there will be immune reaction, they will form a layer on the sensor surface, and the sensor will degrade very fast, it will stop working because it will cover the sensor surface. So, that is why we go for the minimally invasive approach, where we are actually penetrating the needle, microneedle, just below the skin, and we are monitoring from something called as interstitial fluid, ISF or ISF, interstitial fluid. So, I just wanted to give you a background, although I know this course is about AI, we will come to where we are actually using AI, you will see. So, it is called as the interstitial fluid. Okay. So, if I recap little bit, so we know that there are two things, diagnosis and therapeutics. So, in therapeutics you require continuous monitoring, and within continuous monitoring you require biochemical monitoring, and within biochemical monitoring you require continuous biochemical monitoring, and continuous biochemical monitoring requires biosensors, and biosensors can be of two types, continuous biosensors can be of two types, minimally invasive and non-invasive. So, that is where we are. Now, we will see how AI can be used, or AI can help in improving the performance of these biosensors. Now, there are a few other things to note here. So, the origin of how these markers, let us say glucose, they are traditionally present in what type of body fluid? Glucose must be present in what type of body fluid? Blood. Yes, blood. It should be present in blood. How are they present in ISF? How is it present in interstitial fluid? Because interstitial fluid is not, it is surrounding the blood vessels. How is it present there? The answer is here. I will show you a even better figure. So, these are the capillary endothelial cells, or the lining of your capillaries, blood capillaries. There are actually pores that are present on the capillaries. Okay. Now, depending upon the size of the marker, biochemical marker, they leak out of the capillaries. Okay. So, in your blood there are two types, there are two parts, one is the blood cells and the other one is the plasma. So, the plasma actually leaks out of these blood capillaries, and as the plasma leaks out, you have different molecules, let us say glucose. Glucose is a very small molecule, less than 3 kilodalton, so it easily leaks out. Okay. Then you have other middle sized molecules, you can say insulin, cytokines, they also leak out. Now, even larger molecules, antibodies, they also leak out. Okay. So, all of these actually you have a treasure trove, like one of my collaborators from the UK, he likes to say that we have a treasure of markers in the ISF. Okay. You do not need to go to the blood level, you can even monitor them at the ISF level, interstitial fluid level. So, there are certain, so this what is important to note here is the size. So this size is very important because this is where your AI will come into play, okay, size of the markers. So, yes, any questions? So we will come to this later on. So now we know how markers which are present in blood end up in the ISF, and if they are in ISF we can monitor them using microneedle or using non-invasive methods. Just one more thing I wanted to explain. If we go to this non-invasive method here, this is one of the non-invasive methods that we call as reverse iontophoresis. So here actually when we apply an electric field, let us say we have an anode and cathode. So the electric field which is present between these two will naturally drives the ion, okay. All the positive ion will migrate towards the cathode, all the negative ions will migrate towards the anode. Now they just do not sit on the surface, they actually come out of the skin, okay, out of the pores of the skin. So people have shown that if you apply this electric field, the ions will come out of the pores of the skin. And not only that, because these ions as they are moving, glucose traditionally has no charge on it, but as these ions are moving, when there is an ionic flux, they also push non-charged molecules outside as well. So glucose can also be pushed out because of this ionic flow which is present due to the electric field. Clear? This is something which we can look at in a later stage. So if you look at the entire device development, if you want to develop sensors, then the process starts with the design, okay. So this is more of the engineering aspect of the sensors, where you have the design. So how will you design, what are the materials that you use, what type of sensing mechanism will you use, is it electrochemical impedance spectroscopy, is it amperometry, is it corona amperometry, is it pulse voltammetry. So all of these things or questions are being answered at the design phase. Then you have to look at the manufacturing. So if you have made a sensor in the lab, you cannot market it unless the sensor design process or the sensor development process fits with the manufacturing capabilities. So let us say in industrial manufacturing, let us say in the lab you might be able to make up to 10, 20, 30 prototypes, but you cannot market this unless you are able to make thousands of them, okay, thousands, 10,000s of them, large production volume. So for that you have to actually ensure something called as DFM, design for manufacturability, and that is the manufacturing stage. And then once you have manufactured, this is the clinical testing phase, and then finally if all goes well at the clinical validation and your sensor is working well, then you can actually go into the deployment phase. And in deployment again there are certain questions that need to be answered, which is linearity of the sensor. Linearity, what do I mean by linearity? So what does the sensor do? It converts a chemical signal into an electrical signal. So there should be linearity in this conversion. So let us say I have x axis here, and here I have mentioned concentration, okay, concentration of let us say glucose, and then corresponding here over here I will have electrical. So on one axis I have chemical, on the other axis I have electrical. So they will be let us say microamps current. So generally glucose is detected using corona amperometry or amperometry. So here you would have current. So this conversion should be linear, okay. So this conversion should be linear. Why it has to be linear? Because if I take the slope of this line, so this slope of the line actually is giving me something called as sensitivity, okay. Sensitivity is nothing but the conversion factor, okay. So if I have let us say 1 millimolar of glucose, what is the current that I am likely to see, okay. So that is, let us say for one, so if I say that my sensitivity is equal to x millimoles per microamps, that means for every I am sorry, x microamps, it is the reverse, x microamps per millimoles, that means for every millimolar change I am going to see x microamp current change, okay. Or so in that way if I am seeing let us say a certain, I can convert this, then I can convert. So whatever current that I am getting out of my device, I can convert it back into millimoles, okay, because I am interested in the, so I as an engineer I might be interested in the microamps quantity, but as a doctor they have no relation with microamps, they want to know about the milliamps, what is the glucose concentration. So this is the conversion factor. and this conversion factor you get from the linearity. So, if it is linear, will the conversion factor be constant or different? It would be constant. So, if it is non-linear, then it becomes a challenge because it will change for different value. So, ideally you want to have a large linear range. Okay. So, these are some basics related to sensors. So, if you understand these basics, then we can go on to see how AI can be applied. Okay. So, this is where we first start to see the application of AI in sensing. So, if this actually this slide is quite nice. It has been taken from a recent paper in ACS Nano. It says technology roadmap for flexible sensors. It is also applicable to non-flexible sensor as well. So, basically this is, you can say this is the technological. So, why would we make flexible sensors? It is mainly to make it wearable, okay, wearable sensors. So, this is the technology roadmap of a wearable sensor. So, in the olden days there were some sensors that have been developed here to detect earthquake and all these things. Now, as we are moving on into the new century, we want sensors 4.0 or 4.0. And what is this sensors 4.0? Sensors 4.0 is chemistry plus AI, chemistry, electronics plus AI, all of this integrated in a single device. Okay. So, this is where we are actually starting to see the application of AI. So, if you are developing sensors, wearable sensors, there are certain challenges that can be solved very nicely using AI. That is why we have sensors 4.0. So, in sensors 4.0, we want the sensing signal with electronics with AI on top. So, AI is going to look at the sensor data, process the sensor data, make some predictions about the disease and all these things. So, this sensors 4.0 is actually something we call as intelligent biosensors. Okay. Now, what is the technology stack of an intelligent biosensor? This is what it looks like. So, there are 4 stacks in which technology can be developed or implemented. So, the first the sensors are made for the human body. So, in the human body the first stack is actually the sensor itself. So, you can have the microneedle array, which is the sensor, and then you have the sensing layer on top of the microneedle array, and on top of the sensing layer you have the anti-fouling layer. Okay. The anti-fouling layer is to prevent the deposition of different immune reaction foulants, body foulants. Any sort of protein is like a fouling agent on the sensor. So, this is to prevent the deposition of the protein on the sensor surface in order to prevent the sensor from degrading fast. Okay. So, this is the stack 1. So, in stack 1, the first stack, we have the sensor itself. So, engineering wise it requires something called as microfabrication. This is the technology that is required to make the sensors. There are different microfabrication sensor methods. In stack 2, we have the electronics, we have the data acquisition systems which are sitting on top of the sensor, the data acquisition systems. So, these are the electronic chips, ICs, integrated circuits. So, there are many different types of integrated circuits. So, if you are the IC for an electrochemical sensor will be different from the IC that is designed for an EMG or EEG signal and all this. And they also combine communication. So, we can send the data to a mobile or a computer, and all of this actually comes in stack 1, stack 2, instrumentation and continuous sensing. Now, stack 3 comes the mobile app, where you might deploy some AI if you wish, if it is possible, some edge AI. So, generally this mobile is called as the edge device. Edge device in typical AI terminology, we call this mobile as an edge device. It may be the sensor itself, it is not a mobile phone, the sensor itself can also be considered as an edge device. So, ideally you want the AI to be deployed on the edge if it is possible, because AI requires lot of memory, lot of processing power. In some cases it is not possible, but you can also deploy there, and whatever data that you are getting from stack 1 and 2, it is processed in stack 3, and this in the decision making process AI is involved. And what is it answering? when and how much, like I told you earlier. These are the two questions: when to inject, let us say insulin, and how much insulin to inject, and this is actually driving an actuator. This information is given to an actuator. This actuator can be an insulin pump, and this is where you start to see the closed loop system. And this actually, the actuator insulin is going into the body again, and it is affecting the glucose level again. So, this is where you have the closed loop system. Okay. So, sensing, then based on the sensing you are making some decisions, and based on the decisions you are giving the drug, and drug is again controlling the biomarker level. So, this is called as the closed loop medical device. So, this is called as the closed loop medical device. So, this whole process, this is where the loop is closed, closed loop medical device. And on the stack 3 you have AI and software, and the final stack is actually the cloud, where you can store the data. So, here there is also another option. Most of the AI models, let us say deep neural networks, they are very hard to train on edge devices, they require a lot of memory. So, what people do is generally they train the model in the cloud and they deploy in the edge. So, the trained model, like sir was saying yesterday, you can transfer weights. So, you can actually download the weights on the edge device and it works fine. Okay. So, in this way, and you may need to update your AI model frequently on a regular basis. So, this is how the closed loop. So, this process is called as the closed loop diabetes management. Or it is also known as, so in non-technical terminology it is also known as artificial pancreas. So, you have the CGM sensing, this is actually leading to the control algorithm. Control algorithm decides how much insulin to be given, and that actually controls the glucose level, and in this way the cycle goes on and on and on. So, in this way you can make the life of a patient easy. So, this is the sensor and this is the insulin pump. Okay. And this sensor is nowadays whatever is available in the market, it is actually minimally invasive. It is not non-invasive yet. People have tried using non-invasive devices, but the error is not within the acceptable range. Okay. So, they have not been translated well, and there are certain other disadvantages. So, non-invasive sensing has not come into play yet, at least for glucose sensing. So, this is how the device looks like in real life. So, this is a person wearing an insulin pump. There is an infusion set which goes into the body for pumping the insulin, and then you have, so this is a insulin pump as well. This is the glucose sensor. This is this wearable glucose sensor. This type of glucose sensor we have in the lab also, I can show you, and it senses from the interstitial fluid, as I said. Clear? So, this is how the closed loop system works. There are certain challenges to it that you can solve using AI, but we will come to that later on. But overall, this is how you have the insulin pump, the sensor, and they act in a closed loop fashion. Okay. So, this is more of a control engineering problem. So, and this is the so you might ask, why do we, what is wrong with the current, if I measure in blood and I try to take insulin, what is wrong with it? Nothing is wrong with it. The only thing is that first of all, it is a burden on the patient to do continuous monitoring. The second problem is, or the second advantage, you can see if you look at this paper, this is a recent, this is from 2019, you can see that people who are using closed loop, the percentage of time for which glucose is within the normal range is higher than the control group. Yeah, please.
Sir, I mean, what kind of errors these devices can produce? Like,
I'll come to that.
Okay.
Definitely, I'll just discuss it shortly.
Sure. Thank you.
And if you look at this percentage of time again, so this is the normal range of physiological range. So you see that people with the closed loop, they actually perform quite well, or they are consistently higher, they are performing better than those on the control. So there is also, so this is a 6-month randomized control trial, you also have a 12-month data. So in this 12-month also it was observed, the figures were a bit large, so that is why I did not put it here. So if you look at this, it actually shows they actually have people who are actually using this AID. AID means automated insulin delivery, automated insulin delivery. So AID. So people who are on AID, AID is another terminology for artificial pancreas. So different people like to use different terminology. People call it AID, artificial pancreas, closed loop device, and all these things. So they show even much better performance than the people without them. Okay. So yeah, please, Mike. Once you see the sensor, you will realize whether it is comfortable or uncomfortable. It is very light. It is even lighter than a coin. Do we have some devices here? Can we? No, in that box. Can you please show them? Just that's that CGM device, CGM sensor. You can pass it around. So yes, just pass it around and you feel the weight and you will realize whether it is, you feel it yourself and answer your question. Yes, please, yeah. Very good, very good. You should say it in mic. It should be recorded. It's a very good question. I will come to that. That is where actually the AI comes into play. So just say it again so that I understand clearly.
So what is the normal time period between the for the machine, between the input, the response from the actuator, and getting the actual output from the body after the response has been recorded?
Okay, so just to make sure that I clearly understand your question. So you mean that what is, let's say somebody is monitoring glucose.
Yeah.
What is the time difference between change in glucose level inside the body?
Yeah.
Machine senses it and tells the actuator to pump the glucose, insulin.
Yes, and then the final output, like the actuator has already pumped the glucose inside the body, and we have for the time it takes to change the concentration inside the body and it to be, recorded again.
Yes, very good question. I'll come to that. Just 1 minute. Yes, have you all
some inference
observed?
time? I think like she's asking inference time.
Inference time. Yeah. So these are good questions. I'll come to that one by one. So first I will deal with the delay between the blood glucose level and the sensing. Okay, so I'll come to that first.
Sir, will there be insulin infused in it or something like
in the muscle?
So I'm asking in that machine.
In that machine, I'll show you. So here, if you look closely, there is a cartridge here.
Oh.
Right, there is a cartridge. So you can actually change. So depending upon the pump, you can store up to 20 units. If I'm not wrong, 20 units means 20 ml, I guess, 20 ml of insulin inside the machine. Then you have to replace it. The problem, there are certain issues. I will discuss that also. What are the issues with current issues with this? You can store. Yeah, please. Yeah. So he is actually wearing a CGM sensor. He can show you also maybe later on after the class. Yeah, he is actually wearing it, and it's so light that you cannot feel it also. You pass around the microneedle, please. The other one, the polymer microneedle. So it's lighter than a coin, right? Many of us have forgotten about the 1 rupee coin. It's not in circulation anymore, right? So 10 rupee coins are a little bit heavy. So it's almost like a 1 rupee coin maybe.
Sir?
So even the needle is the sensing part is flexible. So if you touch the top, the tip is flexible. So it is this sensor, this one. Yes, please.
Sir, sir, my question is about little bit psychological.
Yeah.
So I have seen a recent research where about this wearable sensors or like wearable watches.
Yeah.
They found that like there is a nocebo effect. Like, there is a negative effect psychologically. They feel that, like, they are not up to the mark, or maybe a kind of psychological trigger.
Yes.
So, like, will this device, can impact that, can create certain kind of psychological problems?
Yes, it differs from person to person.
Yes.
Okay. So that is why the effort is to integrate these sensors into daily wearable things like watch or a ring, so people don't feel conscious. So if it is on the arm, let's say in India mostly we wear t-shirts, so it might be exposed and people will feel conscious that what is, so that's what you're saying,
yes,
right?
yes,
Nocebo.
exactly.
So that's why there is an effort to make, so that's why you can make accelerometers and make it like a band and wear it.
Why like kind of ornaments?
Yeah, like an ornament. And why is it why is it like a watch? It's because to get rid of this nocebo effect.
Yes.
So nowadays, in recent years, there has been effort of making these devices integrated into daily wearable things like rings or watch in this way. Okay, not as a standalone device.
Yes.
It differs. Like some patients, they experience this. That's why actually it is being more and more integrated into daily devices. So that's why you see very less adaptation of wearable EEG systems.
Yes, sir.
So like a band.
I have seen.
Nobody wants to wear that band and walk. So that's why. That's very valid point. Yes. Your question is answered now, I hope.
Sir.
Yes. Yeah.
Sir, what is the refill time for the insulin in that device?
Yes.
Because
so
we store insulin like 4 to 5 degrees Celsius.
Yeah.
And what is the repetition time to refill, or how it will maintain the?
Yeah. So ideal refill time, it varies on the dosage that the patient is taking. So this is actually the ideal generally recommended from what I heard is daily. So every day you have to replace that cartridge. So that is for 1 day. But if for some reason, let's say somebody takes a large bolus, then it can vary also. So depends upon the dosage that, so that cartridge can hold up to, depending upon the pump, it can hold up to 20 ml. So depending upon how much dosage you are taking, that's its lasting. So about your temperature question, I am not entirely sure that how you store it. But generally insulin is stored in fridge in 4 degrees, but while there must be some lifetime outside it also. So where you can actually use it. So in India it is recommended to use.
It's injected in the normal temperature after thawing it. But
no,
it's stored in.
Yeah, it is stored in this. But I don't know how, like what type of insulin it is or how. So daily recommendation, I think it's that you change the cartridge like once in a day or something like that. Yeah. Yeah. Have you seen the microneedle? Microneedle, the square thing. So those, if you touch the surface, it feels little bit rough, right? So these are all small needles. It will not harm you in any way. It will just penetrate the skin. If you press very hard, there is a way to see whether it has penetrated the skin or not. So if on the surface of the skin, if you press it hard, you won't feel any pain. But after removing it, if you see the marks are remaining for more than 2 minutes, that means it has actually penetrated. Okay.
Sir, I was asking about artificial pancreas.
Artificial pancreas.
Yeah.
Artificial pancreas is a combination of all these systems: sensor and insulin pump and algorithm.
So I was asking ki uncomfortable wearing.
Wearing this, wearing the pump. Yes, pump is little bit heavy, I agree. But still the size of the pump, unfortunately we do not have a pump here. It is like the size of a credit card. And so the weight is also almost
so
like
it is
the.
better to test and give why to wear this.
So that also you can do. So you can wear the sensor and you can give MDI. It's called as MDI, multiple daily injections. So because the pump is, the sensor is relatively cheap. The sensor is relatively cheap. Cheap means each sensor, this sensor that we are showing you, it costs 5,000 rupees, and you can use it for 14 days. Okay. So this, now the pump is in lakhs. Okay. So many people don't get to use, or they cannot afford the pumps maybe. So what they do is they use this continuous levels to do MDI, multiple daily injections also. Okay. So but the control definitely is better in the pumps, because actually there are two types of dosage, insulin dosage. If you look into the detail, so there is something called as the basal dosage. Basal dose means there is a background level of insulin always present in our body. Okay. and then when we eat, we have to take something called as the bolus dose. So, background is the basal, and on top you have to give the bolus. Okay. So, this pump actually you can use it to give both. You can give a continuous infusion also, you can give a bolus also. Okay. So, but when you are taking only in injections, then you are actually doing bolus. Okay. Now, in India, doctors might be able to answer this in a much better manner. There is an insulin, because it is tough to give multiple daily injections in India if patient is not aware, or if somebody is living far away, purchasing insulin is difficult or whatever. In India, doctors might be able to comment on this better. There is something called as mixed start. It is the insulin that is given. So, mixed start is a combination of basal and bolus both. Okay. It does offer cover, but of course, the golden standard is this automated insulin. So, there is a data set that we use in diabetes, like if you are using AI for diabetes, then there is a data set called as the Ohio type 1 diabetes data set. It is from the Ohio University. So, if you look at their approach, they take basal and bolus both, whereas in the Indian scenario, our patients mostly take mixed start once or twice depending upon the doctor's prescription. Okay. So, this Ohio type 1 diabetes contains database of type 1 diabetes patient, and the control is very good on this basal and bolus control, and maybe maybe sometime tomorrow we can show as a practical maybe.
Sir.
We can open the Ohio type 1 diabetes. Yeah.
Sir, my question is after like insulin pump, like we are saying the insulin pump. So after insulin is getting the output is given, insulin is getting rejected from the pump, and then it is going through interstitial.
It is going into that absorption route. I am also not sure, but generally it is given intramuscular.
Okay.
So generally people, if we are doing this insulin pump pen, if you are taking the insulin pen, then you give it in the thigh, or even in the
lower
abdomen also.
Yeah.
So here also you are giving in the lower abdomen.
Okay.
Most likely it is intramuscular. I don't know exactly where the absorption happens, but it happens in
it happens through diffusion.
Yeah.
Then,
Yeah.
Thank you, sir.
It's not going into the interstitial fluid.
It is directly going to the
muscle, yeah, muscle or blood, whatever. From there it might go into the blood. Now the people have tried this microneedle approach. It would be good to have a insulin patch instead of insulin injection, but for some reason it has not been adopted clinically. Maybe the insulin absorption through the interstitial fluid is not that good, so it has not. So you can have, like, people have used vaccines. People have tried to see if you can use a microneedle patch for drug delivery for vaccines. It depends upon how the body reacts, how the body is able to absorb. Let's say the percentage absorption in intramuscular it's very good, but percentage absorption through the interstitial fluid will be less. So that's why it's still not yet there in clinical practice.
Sir,
yeah.
Sir, recent study I saw that inhaler also coming into insulin. Like
inhaler, yes. Inhaler has recently been approved by FDA also. It is also coming. Inhaler.
So this much of CGM is not required.
CGM will be required. Pump may not be required.
So that is the tank said that will be removed, right, sir?
Yes. The CGM may not be required, but how much insulin to inhale,
how much intake,
take, that might be required. And also it depends on the dosage of the insulin. Let's say somebody requires 20 units of insulin, it may not be possible to deliver intranasal. Okay, so then you still need injection. Okay, so insulin delivery is quite good clinically, and it is actually the glucose sensing happens through the interstitial fluid. Now there were some questions while we are looking at, there were some questions about the time, right? So if I write time or error, there were some questions about the error also. So in order to address this, so somebody said what is the response time? So there are actually the error or the delay happens at multiple stages. In order to reduce this error, AI is needed. So the first time delay that happens is at the sensor level. Okay, at the sensor level there is some delay that happens, and then we'll see where other places things can go wrong. So that we are engineers, we try to solve problems wherever it happens. We try to guess, or we try to preempt errors where it can happen and then do it. Anyway, so if we look at the interstitial fluid, so in interstitial fluid actually, so these are the sensing devices that you have already seen. Okay, In the market currently there are 3 different types of sensors. One is the Medtronic one, then there is Dexcom, then there is Abbott Freestyle Libre. The one which you saw is the Abbott Freestyle Libre. Okay. There are other sensors also, their performances vary, applications vary. It may not be Guardian anymore, there are much higher versions of sensors. So the Abbott Freestyle Libre sensor, it's called the Freestyle because you don't need to calibrate it. Once sensor actually requires frequent calibration. Frequent calibration means conversion factor will change with time. So that is the first error that can happen, that the conversion factor when you implant the sensor might be different as the day progresses. Conversion factor means, let us say for 1 micromolar of glucose or 1 millimolar of glucose, x microamps might be generated, but as the sensor is covered with bodily fluids, as the sensor is covered with let us say white blood cells or biofouling agents, this sensitivity changes. It is natural, whatever anti-biofoulant you use, whatever anti-fouling agent you use, you cannot prevent it 100%. There is always some sort of a degradation. So this is where the first error happens. The conversion factor changes over time. Now this Freestyle Libre sensor, they have made the sensor in such a way that they don't ask you to calibrate it regularly. Otherwise the first generation of glucose sensors, continuous glucose monitoring sensors, they asked the user to calibrate it twice. So calibrate means whatever sensor we are measuring, you have to do a blood glucose measurement and you have to figure out what is the difference and you have to match it. This is the problem with the first continuous generation of CGM. But as the sensor progressed, like this Abbott Freestyle Libre, and now Medtronic has also come up with a sensor which does not require calibration. So they are marketing that okay, 14 days you wear it, no calibration required. So there are various reasons for it. FDA guideline is FDA actually has suggested, if I remember correctly, it has to have a difference of maximum tolerable error is 10% or something. Don't quote me on that. From my memory, I am saying 10%. So up to 14 days, they are ensuring that it is not going beyond 10%. So that is why they are saying you can use up to 10%, 14 days. Yes. So, so in that respect, the sensors which were asking you to calibrate was better. Okay. So up till now, in my experience talking to colleagues, this one is the best. So
and the grid array device, that was the non-invasive one that we talked about.
Yeah, non-invasive.
So how does that how that device works actually?
So the non-invasive one, that is there are many different non-invasive devices. The one which is which was very close to commercialization, it's actually called as the Gluco Watch. So that is based on the reverse iontophoresis system. So if I go back in slide. Yes. So this is the non-invasive one on the right hand side. So here actually we create an electric field between 2 electrodes. It's very simple. You create a static electric field between 2 electrodes. Now when you have this electric field, you have a flux of ions. All the positive ions will go to the negative plate and the negative ions will go to the positive plate. This is electric induction. So here when there is a flux of ions, when the flux happens, this flux or flow of ions causes non-charged molecules like glucose to also move, to come out of the pores. So it's like they are forcing, okay. But how well they are forcing, it's actually there is a question mark. So that is why the non-invasive devices have not had acceptable accuracy for clinical use. So they might follow the trend that okay, if glucose is going down, non-invasive devices will also sense glow down. If it is up, then it might go up. But the exact level you cannot use it for clinical decision making. So clinical decision making requires very low, like a certain amount of tolerable error. So they are not within the range of the tolerable error.
And then how frequently those flux are actually induced?
So this flux actually, since we also worked in reverse iontophoresis for some time. So what we do is you turn on the electric field for let's say 5 minutes, then you start your sensing. So whenever you want to make a reading or whenever you want to take a reading, you have to create a flux for 5 minutes let's say, and then switch off the electric field and take the reading.
But so I'm still trying to map it to the grid device that we just saw. So
yeah.
Is it the same device?
No, different. It's different.
The grid one? Not this one. Oh, okay, so what is this device then?
Which one?
So this microneedle
Microneedle is this one, minimally invasive.
Oh, this is still minimally invasive thing.
Minimally invasive.
So again, this one does this have data storage capability or?
Right now there is no electronics mounted on it, but you can show the other one. You can also.
Yeah,
you have shown.
other one I have seen. So
yeah.
again, so it has to be used in I mean along with the data, I mean data reading or the electronic device that you talked about.
You have to mount electronics on top of it. So the white device, white circular one that you have seen, if you open the cover, there is electronics inside it. You can see it also transparent. Yeah.
Got it. Yeah, I think then it makes sense, right? So, I mean, I was asking about this. Thank you.
Okay, shall we move on? Yeah. Right. So, so the first error that happens is here. So you can see. So here actually, as the so this is the first error that happens here. The error is due to the change in conversion factor. The other error is due to delay. Okay. So what is the delay here? Okay, few more details about glucose sensors. Those of you, I put these slides because I realized many of you are from biotech background, so you may want to know these things. So these are all first, second, third generation sensors. These are called as the enzymatic sensor. Okay, enzymatic or glucose oxidase sensor. The market ones are also enzymatic sensors. All the market sensors. Why they are actually using enzymatic sensor? Because enzymatic sensors are highly selective towards glucose. Okay, you won't get any or you will get very less interference from other enzyme or other analytes. Anyway, so this is the first place where error happens. So what happens here, if you look at this diffusion, is in engineering we call it as, or even biology also, you call it as diffusion. So as the biomarkers or as the molecules are diffusing from the blood to the interstitial space, there is a, so this process of it's actually called as, they are actually modeled as a 2-compartment model. So biophysical modeling we call it as 2-compartment model. So there is one compartment is the blood vessel. So this is the blood vessel, and the other compartment is the, let us say, compartment A, and compartment B is the interstitial space. So as the molecules are moving from the blood vessel to the interstitial space, there is actually diffusion happening, and there are certain diffusion constants. Okay, and this diffusion process is not a smooth process. So there is actually a time delay which happens here. So this is the first place where actually delay happen. So there is people have actually measured what is the typical delay. The typical delay is between 10 to 12 minutes. It can, in certain conferences I have also heard that this delay can go up to 15 to 20 minutes also. So there is a physiological delay of 10 to 12 minutes. Means what I want to say is, let us say my glucose level changed at time t equals 4 p.m. Now this change I will observe in the sensor at 4:10 or 4:12. Okay. So this is the first place where the error happens, and this physiological delay actually causes the if I am making some decisions using based on these glucose levels, then it makes it difficult to make decisions. Okay. So there are two scenarios which might happen. One scenario is that there might be a delay in the insulin injection, okay, and then that delay will cause hyperglycemia, or I might, if let us say the glucose level is going down, then I might incorrectly measure a high glucose level because the reduce is yet to be discovered because of the delay. Then there might be hypoglycemia also. If I give too much insulin, then it will be hypoglycemia. So this delay is very crucial to fix, and this is where actually AI comes into play. So this is the engineering approach to artificial pancreas. So in this engineering approach, this looks like a control systems diagram. So control systems diagram, you have, control systems are used in plants. So you have an objective, and what is our objective? Our objective is to maintain glucose level between, let us say, 70 milligrams to 120 milligrams per deciliter. So that is our objective, and in order to maintain this objective, we have a controller. Controller is the algorithm, it is the AI model, okay, and then we have the insulin pump which is controlling, and then we have the body. So this is the body. So this entire thing is the body. So within the body, if you look closely, one box is there which is called this actually tells us the response of the body to insulin, okay, insulin response. So if I am injecting insulin, how fast insulin is acting on the body or on the glucose level. Then we have the glucose response. Glucose response means if let us say I have taken the meal, how fast the meal leads to change in glucose level. So these are two different blocks that I need to consider. And then in the feedback path, this is the feedback. Whenever there is a connection between the output to the input, we call it as a feedback. So in the feedback, we have the glucose sensor. Okay. So let us say, so where is this physiological delay happening? The physiological delay is happening here, Ym. In Ym, sorry, YIV. So this is where the physiological delay is happening. So you might have, so it might be YIV plus T delay. Okay, so there might be some delay before you can sense the glucose level, because glucose sensor is minimally invasive. There might be physiological delay, and this delay actually, if I have a delay here, it will delay all the entire loop. Okay, so if I design a PID control loop, so in the olden days, not when I say olden days, it's not very old, like maybe 10-20 years back, 10 years back, all the insulin pumps, they operated on PID control loops. Proportional, integral and derivative control loops, PID control. So over there it's very hard to tune the PID loop. If you have a delay, if you have an uncontrollable delay in your system, if you know that the delay is fixed, then it's okay, but this delay might change. Let's say somebody is wearing the sensor for 14 days, so the delay might be same for few days in the beginning, then it might become more, and 10 to 12, and then the entire PID control actually is very difficult, it goes out of the window. So people have actually tried different approaches. The earliest approach is PID control. Then people have also tried to incorporate this delay using the beta cell bio-inspired modeling. So in our insulin we have beta cells in the islets of Langerhans which secrete insulin. So people have tried to make a biophysical model, mathematical model of the beta cells, and in recent years, of course, we want to use deep learning approaches. Okay. So people have shown that deep learning approaches, deep learning models are very vast models with large number of parameters, and they can incorporate many different variations. So here, if you are using the PID loop, you are considering only one variation, which is due to meal. So glucose level can happen, change in glucose level can happen due to meal, it can happen due to physical activity. Let's say somebody is doing aerobic, anaerobic, different types of physical activity will affect the glucose level differently. Stress can also affect to certain extent, sleep cycle, circadian rhythm can also. So there are many different factors which are affecting your glucose level, and all these factors to some extent can be covered or tackled using the deep learning approaches. So should we take a break or should we continue? Yes. So if you want to take a short break also, it's fine, we can
Sir,
take a short break.
very basic question, sir.
Yeah, please.
Sir, sir, what about the obese people? Because the fat is more stored there. So
I agree. So perfectly. So that's why sensor is being implanted here.
So
So they have carried. So previously, the recommendation, if you see in the old like previous diagrams, the sensor is generally in the abdomen.
Lower abdomen.
But as things evolved, nowadays they are recommending you wear it here, on the biceps.
Okay, there is the
triceps.
The fat cells are less there.
Yes. Yeah.
Okay, thank you, sir.
Okay. So should we take a break or should we continue? We should take a break. Okay. We'll take a short break and then resume from this slide, because there are a few more slides also we'll discuss. Okay, we are back again. I hope we had a good discussion and a good break, and without discussion actually it's hard to understand also. So please feel free to ask questions. It actually enriches the lecture and it helps us in both ways. I also get to see new perspectives, and you also get to learn few things. So anyway, this is where we had stopped before the break, and we saw where the problem arises in this artificial pancreas. We had addressed the first delay or the error that can happen, which is the physiological delay. Now this physiological delay, it varies from patient to patient, or it may vary slightly from individual to individual. Just wanted to recap this technology stack again, where you have in the first technology stack you have the sensors, in the second stack you have the electronics. So first stack sensors, second electronics, third you have the AI models deployed on the edge device, and finally for data storage and cloud you have cloud for data storage. So these are the 4 technology stacks that are needed if you are actually planning to develop an intelligent biosensor. And you can work at different levels. Some people prefer to work at stack 1, so they are more into sensor development. So this is mostly electrochemists or chemical engineers. They are more into developing materials, different fabrication methods. Now not all the fabrication methods, microfabrication methods are implemented or scalable for manufacturing. So some people look into that. Some people are more into electronics. They make chip designs, integrated circuit design, very low power devices, low noise devices, and some are into the stack 3 purely AI. But generally whoever I have seen in the domain of biosensors, they work at least in 2 domains, 2 technology stacks, either 2, 3 or 1, 2. So and finally the cloud computing, where it is mainly it is used for data storage and model training if required. So shall we proceed, or we have any more questions? Mike. Yes, please.
Sorry. I think the question was the device, the cesium device that we were looking at. So if let's say 2 person is wearing the similar cesium devices,
yes,
can both be scanned using a single reader?
That we haven't tried yet. In theory, yes, because we have a single reader in our lab and we have tried with multiple sensors. So I don't know whether you can be able, it is possible to do it simultaneously or not, but at different times you can do, yes.
Different as in like one by one after another?
You can do it, not a problem.
Okay. So I mean, I think that is something we have to maybe take care when we productize this.
Yes, so this actually is not something which we have made in the lab. The reader is actually, so as I told you, the sensor which I have shown you is the Abbott Freestyle Libre sensor.
Okay.
So their model is that you actually have multiple sensors. So the sensor is recurring cost and the reader is a one-time thing that you buy. Okay, so that is their approach, the business kind of.
And the data, imagine I'm using the same reader to read the data from 2 different sensors.
Yes.
So will it be counted for one patient or?
So the way to look at the, so for example, if you want to look at the Abbott Freestyle Libre sensor data, there is a package, there is a software called Tidepool. So while uploading in Tidepool, you can log in under different names and upload it. So the Tidepool will upload actually 8 hours worth of data. So how you segment that data, if you are aware that at this time I took this person's data and this time I took this person's data, you can segment it. So it's possible.
But that's not automatically provided
no, that's
by
not
these readers. Okay, all right, thank you.
Right. So this just, I think you have seen these devices already in the class. So microneedles, this is the magnified image of the microneedle that you may have felt using, or you may have touched it. So this is how it looks like. So the microneedle that you have actually, this is actually gold coated. This microneedle is I think carbon coated, if I remember correctly. So these are the fine microneedle structures that you can see here, and they can actually be used to penetrate the skin and monitor analytes from the interstitial fluid. Okay. So now that we all, so generally this kind of device we have made for low density monitoring, and these microneedle are therefore high density monitoring. High density means spatial density. So this is how actually it looks like. Overall the system looks like this, a closed loop diabetes management platform where you have the patient type 1 or type 2 BD. They might be wearing a sensor, and the sensor data actually goes into an app. So here we have shown Bluetooth, but about Freestyle Libre, as you all know, they work on the NFC communication. So Bluetooth is more of a continuous. For NFC you have to repeatedly scan, you have to scan the sensor. So once it goes inside the app, from there it actually goes to the cloud. So the AI model can either sit over here, the trained AI model, or it can also run in the cloud. For security issues, generally people prefer to keep it in the ideal scenario is where you are training and forecasting in the app itself, because it's more secure. You don't have to send the data. But still we have to think of limitations of space, computing power and all these things. So here you can actually, you have the cloud for data storage, and over here you can also do forecasting. So there are two types of applications that AI is being used here in closed loop diabetes management. First is the forecasting, and then using this forecast also you can do the bolus and basal dose estimation. Okay. So this forecasting actually requires, although it seems very simple that okay you are following a certain trend, but this glucose level can be affected by multiple factors like we discussed earlier, by meal, by physical activity, by circadian rhythm and stress. So all these factors cannot be modeled mathematically in a simple model. So you require a deep learning model to capture all these variations. Similarly, insulin dose, when a person is taking an insulin dose, the response to this insulin dose, the conversion factor, how well the insulin is actually absorbed by the body, this also varies from person to person at a very small level. Okay, so these variations can again be captured by AI models. So traditionally the approach has been that people use one AI model for forecasting, another AI model for insulin dosing. So that's why if you look into the literature, if you look at papers, so you will see papers for insulin dosing only and papers for glucose forecasting only. So they treat both of this separately. Now application wise it is very time consuming and tedious to have two AI models running together and they are syncing them, and it's very difficult. So in recent years people have started looking at the entire application together, so that you have a single AI model which can do both forecasting, and based on this forecasting, whatever forecast you are getting, you are actually using that for insulin dosing as well. Okay. So just to simplify the previous diagram, we have removed the app and the cloud here. Now you can see the image or the diagram or the system in a much more clear manner, clear fashion. So here you have the CGM sensor, and this CGM sensor, so these are the factors which are affecting your glucose level, physical activity, meal, then you have insulin. So primarily the AI models that we have worked on or we have developed, we are actually considering these three factors mostly. So physical activity level, physical activity can be captured in terms of number of steps, altitude covered. There are also other factors like heart rate. So all these activity you can actually capture using your wearable devices. Nowadays we have Fitbit and other wearable devices that can be captured. Then we have the meal information, and then we have insulin. So regarding these two, so this is done automatically. This is automated because you can use the API of the wearable device to pull the data from this and incorporate it into your system. But about meal and insulin, most of the time patients have to manually declare it. So if they are using the currently available artificial pancreas, they have to manually declare it that okay, I am going to do exercise in the next 1 hour, or even or let's say somebody has taken some meal, they have to declare that okay, I have taken meal of this much carbohydrate content. So all of this thing, there is a bit of manual intervention, it's not completely automated. So similarly, that's why in technical terminology there are two types of artificial pancreas. So one is called as the hybrid artificial pancreas. Hybrid means there is little bit of human intervention required. The patient has to declare meal, the patient has to declare the physical activity in some cases, and in some cases they also have to declare the insulin as well, although insulin is being automatically given. So these most of the systems nowadays, they are actually hybrid artificial pancreas. The goal is to go for complete closed loop, so where the patient doesn't have to declare anything, everything happens automatically. Okay. So the dream is yet to be achieved. People have tried to do it in many different ways, but it is yet to be done. So here over here if you look at this system, so there is a now let's see why forecasting is needed. Okay. Forecasting is needed because all of us, depending upon person to person, patient to patient, the physiological delay may vary slightly. Okay. Now, generally if you are an electronics engineer, you are quite used to high frequencies, right, kilohertz, signals changing within milliseconds or microseconds, but that does not happen in the body. If you look into glucose level it takes minutes to change. It is a very slow changing glucose level. So, if you have delay, if you are let us say if you are giving insulin, then depending upon the type of insulin that you are giving, maybe it is fast acting, slow acting, this actually also affects, it is not in a matter of seconds, but in a matter of minutes. So, that is why you have to actually forecast the glucose level in advance to preempt the physiological delay and ensure that the forecast is correct, because based on this forecast insulin dose will be given, and based on the insulin dose glucose control happens. Okay. So, these are the typical time series forecasting methods that people have used in AI. So, recurrent neural networks, LSTM, GRU, and in a very recent network that has come out is called as the neural basis expansion network. Okay. Neural basis expansion network. So, there are some other advances to this as well. So, the advantage here in n-bits is that this actually is interpretable to certain extent. Okay. Interpretable. Now, there are some of course where to use LSTM and GRU. If we had a little bit more time, we could have discussed more in detail, but there are pros and cons of both using LSTM and GRU, and similarly there are also pros and cons of using n-bits. Okay. Both of this actually they require enhancement, some additional work is required. So, initially when we look like our lab, we started working in the domain of glucose forecasting. So, we wanted to see how well this forecasting, how it works, what is different from the Indian in the scenario that we have in India, how is it different from abroad. So, if you work in this domain of glucose forecasting, you require data obviously, and data you can get of, there are two types of data. So, one is the most popular one. So, nowadays there are a lot of data available. So, this one actually, this is called as the Ohio type 1 diabetes data set. So, this data set actually it has there are two series of data set, one is in 2018 and the other one is in 2020. Now, 2018 and 2020 they have used different models of the sensor, and in 2018 I think they capture some more information in the 2020 version compared to the 2018 version. So, overall you have around, so in this one you have 10 to 12 individuals in both the data sets. So, very less, but yet it is enough for glucose forecasting. So, here you can see over here, this is they are using actually the AID device, automated insulin delivery. So, this pump 630G is an insulin pump, and then they use different sorts of sensors. This Empatica is a wearable band, like we have Fitbit, we have Google, different bands for monitoring physical activity. So, Empatica is a much more advanced band which not only gives your heart rate, and nowadays you have these Whoop that people are using, right, for physical activity. So, you can actually use it for measuring stress also, Empatica. So, different actually bands are there and different sorts of individuals are there, but you see more or less the age is between 20 to 40 and the data set is also balanced. If you look at the gender, then it is more or less balanced. So, it is a good data set to start with. Now, and anyway, getting data sets where you have closed loop diabetes, people are using like insulin delivery as well as insulin sensor at the same time, it is very rare. So, that is why Ohio T1 diabetes data set is quite popular for people who work in this field, because it has sensor as well as automated insulin delivery or pump based data set. So, this is how the data looks like. You have mostly we are interested in this CGM. So, this is your basal rate that I told you about, basal insulin and bolus insulin, and this one actually there are certain, so this is mostly physiological data. You have acceleration, steps and all this to measure your physical activity, and you also have insulin information. So, this is actually insulin information, bolus events. So, you can see bolus, okay, and basal is told you, and basal is continuous, it is always there in the background. So, it is always there in the background. very small level, always there in the background. Now as the person is taking meal, they also have to calculate how much bolus dose is required, and they take the bolus dose. Okay. Anyway, so what I want to highlight here is, let us say I want to take this bolus dose over here, then I cannot take this bolus dose. So in order to unless I calculate what will be the dose, what will be the quantity, how many units of insulin required. So in order to calculate that, I need little bit of background, okay, little bit of background of what was my previous glucose level, and people also have to calculate. There is a manual method of calculation. They also have to calculate something called as CF, conversion factor. So they have to calculate how much insulin is required for their body. So there is a back of the envelope, means rough calculation. If somebody is taking insulin and they are supposed to take bolus, then doctor gives them a rough calculation method, and using that they actually calculate that. So it is based on their weight and other things, but in order to make it more personalized and better control, so actually we need this kind of AI based methods. Not only that, we also try to collect some data. So this is something which we collected here in Odisha, SCV Medical College. We tried to collect up to 12 individuals. So out of these 12 individuals, there are 6 type 1 diabetes patients and 6 type 2 diabetes, and then we also balance in terms of gender and all that. So this was our system. So we use the Abbott Freestyle Libre, but in addition to that, we found out a device which is called as the Bluecon device. So this Bluecon device actually converts the NFC signal into a Bluetooth. So your patient doesn't have to scan all the time. So it's actually continuous all the time. And then we have the physical activity monitoring device also. And currently we are still collecting more and more data. And I wanted to show you some results also. How well this forecast is working. Maybe I will show you later on. It's not in this slide, but I will show you later on. Anyway, so but I will show you the forecasting that is done on this data set. Okay. So this is how you have to actually prepare the sensor. So in this over here, you have the Freestyle Libre sensor, and on top of the sensor, this is the Bluecon device. So this Bluecon device converts NFC to Bluetooth. Okay. So it converts NFC to Bluetooth, and then you have to cover it up. You can cover it up, or you can also leave it. The sensor itself is waterproof. Okay, just for the convenience of the patient, we sometimes cover it up, but it's not actually required. And then the patient has to take an image of the meal. Okay, so we also developed some AI models which we are not going to discuss in this class, but using these AI models, actually the AI model will estimate what is the volume of food and calorie content, specifically what is the carbohydrate content, because this carbohydrate content is actually causing the increase in glucose levels. So this is the first network that we developed for forecasting. As I told you, this network actually, in this network we have used a combination of LSTM and GRU cells. Okay, this is one of the earliest network that we developed. These are my inputs: the past CGM level, past insulin, physical activity, and also meal that the patients are taking. And here we have actually used this WD net. We call it WD net because we have gone for a very wide deep approach. Wide deep means not all inputs are going through the same number of layers. Okay, so there are certain inputs which require more processing, so they go through more number of layers, and there are certain inputs they go through less number of layers. So using this, actually you can forecast the glucose level in advance, because this forecast will again be used for insulin dosing. So you are not, just what we were discussing just beforehand, we are not doing the insulin dosing based on the current level, but on the forecasted level. So this work is actually published. So what are the metrics, how we actually judge whether the forecast is good or not? So these are typical AI metrics: root mean squared error, mean absolute error, but this is something which is specific to glucose sensors. It's called as mean absolute relative difference. Okay, so anyone who is working in glucose sensing or any type of sensor, they use this MARD, mean absolute relative difference. This is the industry sort of metric that is used. In this one, they want to actually using this MARD, they construct something called as the Clark grid error. So I will show you this also, Clark grid error. So this MARD, ideally if you want to use it, if you want to commercialize your sensor or your AI model, this MARD should be less than 10%. So that is the ballpark figure. questions? Yeah, please, Mike, please. Yes.
Sir, I had question
Please,
on,
yeah.
I think on the previous slide. Can you please?
Yep.
Oh, so you said you had some model which kind of calculated the carbohydrates out of the food.
Yes, yeah.
So which data set that we used to train that?
That
model?
is actually we had, so there are some food based data sets from abroad, from Switzerland we got, from Indian food data set also we have, and we also curated some of our own data sets that there. So from that AI model will actually do mostly your CHO calculation. So in that data set we have actually have different types of food, and from the container you can actually estimate what is the volume of the food, and then what is the calorie content. So how much carbohydrate is there, protein is there, and all these things. So there is a data set. Yeah.
But for example, Indian foods, if we take the example of bread,
yeah,
there are several constituents of that, right?
True.
And if it's made of different constituent, from the image we cannot detect that. Okay,
yes,
it's made up of that. So
absolutely. So for that, because we did this trial in Odisha, so mostly I also said that we curated some of our own data set, because in Odisha we have a specific way of making foods.
And
so based on that we have
and is that data set public or?
No, we haven't made it public.
Okay.
But
Thank
we
you.
can share it with you, no worries.
Sure.
While sharing the slides I can add.
Sure. Thank you.
Right. So there is a reason why we haven't made it public, because we are still validating it clinically. So once the validation work is complete, then we intend to make it available publicly, because our clinical testing is still going on. So we have tested it in a small number of patients, like I have this data set that I have shown you. It's only 12, right? 6 type 1D and 6 type 2D, but we want a bigger number. So still we are collecting data on this. So this is the Clark grid error, which is based on the MARD, and in this Clark grid error basically you have on the x axis the reference blood glucose level, and then you have the measured blood glucose level. So this glucose level is measured by the sensor. So ideally you want, so what is the ideal scenario in this Clark grid error? Where do you want your sensor to be? An ideal sensor will be where? Straight line, right? So this is your ideal sensor response, straight line. So whatever, let's say if it is 100 here, it should be 100 there as well. Okay, but in real life it doesn't happen. So that's why you have these different areas. Closer to the straight line, the more preferable it is. So that's why we have different areas A, B, and C. So A stands for clinically accurate, B for benign errors but still clinically acceptable, and C for overcorrection. C is also acceptable, but when you are submitting this data to any regulatory agency, they look at what percentage of points you have in D and E. So that will decide whether your device can be used or your sensor can be used or not. Okay. So ideally you want 90% of your points to be within A, B, and C, not beyond that. So these are the forecasting results. So this is again here where you can see here. So there are two plots here. One is the actual data point, and then the black one is the predicted data point. So if you look closely, there is a slight delay between the, so this is due to the model making calculations to do the predictions. So there is another delay here. So one delay is that you try to forecast to avoid the physiological delay, but again when your model is making these predictions, of course it requires some time to compute, and that's where you are actually having some delay as well. So ideally you want to reduce this delay. So if you look at this, if you look closely, then this particular model where you are using only LSTM and GRU or a combination of both, you want to, we have two issues I will say here. So the first issue is that of the delay between the real and the forecasted level. So we want to reduce the forecasting delay. So this is the forecasting delay, and if you look closely, then the model is not performing very well when it is actually very low or very high. So in the peaks. Okay. So ideally you want to match these two. So this was the motivation for looking at other time series forecasting methods. Okay. Anyway, so there are three prediction horizons. One is 15 minutes, 30 minutes, and 1 hour. So 15 minutes is the minimum forecast that you need to avoid the physiological delay. You can expand your forecast to 30 minutes and 1 hour to incorporate glucose dynamics. So if somebody is taking insulin or the glucose level, if somebody has taken food, it's not going to change instantly, it's going to change very slowly. So this change, that's why when you do go for a fasting blood glucose, or if you go for something called as GTT, does anyone know what is GTT? Glucose tolerance test. So glucose tolerance test is also done to estimate whether a person has diabetes or not. So they give you a fixed amount of glucose and they measure your glucose spot measurement 1 hour and 2 hours. So it is expected that after 2 hours you will have normal glucose level. So glucose is completely maintained. So the glucose homeostasis takes up to 1-2 hours too. So that's why you have forecast up to 1 hour as well to incorporate that physiological aspect as well. Okay, right. So these are the real figures over here. So you can see that what I wanted to show you is the physiological delay, but here you can see the MARD is still high for 60-minute prediction horizon. It's not less than 10%. It's very hard to achieve less than 10% for 1 hour prediction horizon. Most of the papers that I have seen, they are still close to 15% MARD for 1 hour prediction. Anyway, so we have tested in different clinical data sets. So this is how the Clark grid error looks like. So this is how the typical you ideally you want all your points to be in A, B and C, but as you increase the prediction horizon, you end up having some points in the dangerous region, which is E and D and E. Okay, so this is what is also acceptable to some point. So like I told you, up to 90% of points in A, B and C is still okay. You will never get all the points in A, B and C. So you will always end up with some points in C and D. So but these are like outliers you have. Yes, so this is something which is interesting. So this specific model we actually evaluated let's say you are training. So should we train your model once and keep on using it, or should you update it on a regular basis? So here this plot actually shows that if you go for a personalized approach or a regular update approach, your MARD actually keeps on reducing, or you are able to maintain the MARD well. But if you do not do that, your MARD will eventually increase. So this is actually in days. Okay, so each test set is actually 5 days. So like this, test set 1, test set 2, test set 3. So if you update your AI model after 5 days, it performs well. Otherwise, if you do not update, the MARD actually keeps on increasing. Right. So this is the comparison with existing work. So these are all these work. Actually, one more advantage of using, or one more motivation for using this Ohio type 1 diabetes is that if I collect local data, then I may not be able to compare my performance with others, but Ohio type 1 diabetes is a standard data set, like you have MNIST or any other image processing data set where people compare. So like I told you, if you look at there are only few works which have got sorry, this is time lag less than 10%. So here also it's actually 15%, but where we want to reduce is this, the time delay. So as you increase the prediction horizon, so it starts with 5 minutes for a for a prediction horizon of 15 minutes, the time delay, the forecasting time delay is 5 minutes, but as you go on from 15 to 30 to 60, the time delay actually increases. So ideally you want this to be less and less and less. Okay, so that is the reason behind forecasting framework 2. So in this forecasting framework 2, we use something called as NBITS, neural basis expansion network. So neural basis expansion network was actually proposed by one of the pioneers of AI, Yoshia Bengio, long time back, not long time back, around 2018, 2019, or even later, I think, I exactly cannot remember. So it was a univariate forecasting model. That means you can only forecast one point, or you can take only one input and forecast one point, and it looks like this. Without the attention layer, it had 2 fully connected layers. Okay, in order to enhance the MARD, let's say we are using this for glucose forecasting, we want the forecast to be as accurate as possible or as close as possible to the actual one. We started using multi-head attention layer. So this is where we did some changes from our own side, where we actually incorporated this multi-head attention, and then we developed this backcast and forecast. Okay, So the backcast is like a feedback which goes back into the model, and then it processes the backcast. So along with other inputs, you have the backcast as well, and then it makes the final forecast based on backcast as well as the current data. So in this way, actually, you can actually develop. This we call it as. So this is the original paper. So around 2019, which introduced n bits, univariate n bits with fully connected layer. But you can enhance the performance of this univariate layer. You can make it multivariate. You can also introduce multi-head attention, and you can make some nice changes to this, so that your forecasting becomes much better. And here you can also add interpretability. So let's have a look at how you can add interpretability over here. So interpretability means if I am getting a certain glucose forecast, you can answer why you are getting this. Okay. So this particular network actually has enhanced interpretability. That means I'll show you how we do this interpretability. Then it has very less prediction lag because of the backcast. The prediction lag is fast. The calculation is not that difficult, and the prediction lag is less. So if you remember in the previous network for the 60 minutes prediction horizon, the lag was 40 minutes. So we can have a look, and the attention layer actually enhances some performance as well. And there are many other advantages. So if you look at this point here, so if you look at the same data set, Ohio clinical data set, 60 minutes, MARD is around 12.84. We will come to the lag later on. So overall, we observed that the performance is less than 10%. The MARD is less than 10% for a prediction horizon of 30 minutes. Okay. So this is how the plot looks like. Its performance. It is actually in previous plots. If you notice, it was not doing well in the peaks. Now using this new network, the framework 2, actually it works well in the peaks and as well as in when it goes down as well. And it is true for all prediction horizons, whether it is 5 minutes or 30 minutes or it is 60 minutes. Okay. So this difference is still, there is some lag there, but we can see how much the lag is. Okay. And this is the Clark grid error. So most of the points are in A, B and C. Even for 60 minutes, if you remember, there were some points over here in D and E for the previous network, but here you do not observe any points in D and E. Okay. It is the same individual, same person. Right. Now coming to the crux where we really see the advantage. So from 40 minutes, we brought it down to 15 minutes. So prediction lag actually reduces massively. Okay. And this actually helps a lot when you are using it in real time, when a person is using it in real time. And up to now, if you look at the previous work also, it's better than previous work so far. Right. Coming to the more important aspect, which is the interpretability. Interpretability in time series forecasting is actually done. We have seen interpretability in AI models, in images. So it generates some sort of a feature map, and it tells you which, let's say in genomics, when you are using genomics for in pathology, so you have different, you get a feature map. So here in time series forecasting, there are actually two ways in which you can implement interpretability. So interpretability actually was, there are two components. One is called as the seasonality and the other one is called as the trend, seasonality and trend. So these are two components. So seasonality and trend. So seasonality is more of a long term, long term changes. It captures long term behavior, and trend is more of a short term behavior. Okay. So when you are interpreting a certain forecast, you can look at which one is dominating, whether seasonality is dominating or trend is dominating, and whichever is dominating, that is the reason for your forecast. Okay. So this was first discussed in around 1990. It's a statistical paper here, Journal of Official Statistics by Robert Cleveland. So they first developed this STL approach for looking at population data. So if they see that okay, certain disease is going up and going down, let's say in winter we have flu, then the seasonality is causing the increase in occurrence of cold or flu. So in this way actually time series data you can actually interpret, you can put interpretability, you can interpret time series forecasting using trend and seasonality. So these are different mathematical parameters. So in this particular model, because of the forecast and backcast, you can introduce this interpretability in the model, and you can look at this plot how interpretability happens actually in the glucose forecast. So if you look at the black line, this is the original data set and this is the forecasted data set. The blue one is the forecasted. That is why you see a delay between these two, okay, shifted, slightly shifted version. Now let us say I want to see what is causing this peak, why there is an increase in this peak. So I can break it down into two components, trend and seasonality. So I can say that at this point where I am seeing the peak, it is because of the seasonality component, okay, and the trend is down. And similarly, let us say, so overall in this figure, if I observe closely, I can say that I can see that the glucose level is going down, okay. It is going down because the seasonality is dominating over the trend. So seasonality is more dominant over the trend. So trend captures short term behavior, seasonality captures long term behavior. Okay, so this is how you can introduce interpretability in time series forecasting. Okay, so all this you can also evaluate how if you are planning to deploy this model in edge devices, then you can look at flops also, the floating point operations per second. So G is for giga floating point operations. So this model actually leads to acceptable amount of flops, okay, floating point operations per second. So this actually helps us determine whether we can implement this model in a edge device or not. So whether you can deploy this in a microcontroller or whether you can deploy this in a ARM processor or not, because every processor has a certain flops rating, and based on that, if it is if the number of flops that your model is taking is less than the number of flops that your processor can handle, then you can deploy it. If it is more, then you cannot do it, okay. So this type of analysis can also be done. And in relation to this, we have published these works. So in order to conclude, so we can say that physiological delay between blood glucose and interstitial fluid glucose is the crux, is the reason why we should do forecasting, okay. And then high fidelity forecasting is needed to prevent hyper or hypoglycemia or incorrect insulin dosing. And finally, interpretable glucose level glucose forecasting actually helps in increasing adaptability or trust, as always in other fields as well. So in imaging also you see that if you have interpretability, the doctors consider it more, they are able to understand this. And not only that, if I look at the glucose forecasting, so this actually helps me understand why a certain why let us say I am looking at my own glucose behavior and I have these components seasonality and trend, I can interpret my own physiological behavior from the trend and seasonality components. Okay, so I can know why my glucose level is spiking at a certain point if I break it down into two parts. Okay, maybe in the morning I have taken breakfast and I am starting to do work, so that can be, I can correlate my glucose level with my daily activity. Okay, so that is why interpretability is very useful, and it is also useful for doctors, they are able to actually judge and or advise patients based on this. Okay, so I think this brings us to the close of this talk. Ideally this was, and I must actually acknowledge my team and my funders as well, and there are references also. These are a lot of papers on this in this domain, so which you can refer and you will have access to this. Anyway, so I don't know whether I think this lecture actually took more than expected, so don't worry, we'll discuss, I mean if you we'll discuss with the team and see if the number of hours, required number of hours are there for this for the day. We'll stop, so we can stop here for today and we can continue the next lecture next day. Thank you all.